Right now, you are moving about 230 kilometers per second around something you cannot see, something that lies 26,000 light years away. You've been doing this your entire life. Your parents did it. Every ancestor you've ever had did it too. Every human who has ever lived. Every star you've ever seen in the night sky. All of it. Roughly 200 billion stars, clouds of gas, planets, everything in the Milky Way, all slowly, patiently orbiting the same invisible center. At that center is a supermassive black hole. It has about 4 million times the mass of our Sun, and for most of human history, we didn't even know it existed. Tonight we're going to trace the story of Sagittarius A, the invisible center of everything we know, the quiet, dark heart of the Milky Way. Let's begin. For thousands of years, people looked up at the night sky and saw the Milky Way as a soft band of light stretched across the darkness. Faint, blurred, beautiful, just light. By the early 1900s, we finally understood what it was. A galaxy, spiral-shaped, vast. With us living far from the center, about 2/3 of the way out, we assumed there must be a center, a dense region where stars were packed closer together, brighter, heavier, but nothing special, just more stars. The problem was visibility. Between us and the center of the galaxy lie enormous clouds of gas and dust. They block visible light almost completely. If you point a normal telescope towards Sagittarius, you don't see stars, you see darkness. For centuries, the center of our own galaxy was hidden from us. That began to change in the 1970s. Radio telescopes started scanning the galactic center. Radio waves can pass through dust, and what they found was strange. A powerful source of radio energy, compact, bright, perfectly still. Too bright to be normal starlight, too small to be a cluster of stars, too concentrated to be a cloud of gas. They named it Sagittarius A after the constellation where it appears in our sky. Something massive was there, something invisible, pulling everything around it. But you can't see a black hole directly. You can only see what it does. As we prepare to journey millions of light years away to witness this cosmic marvel, let's ground ourselves for a moment. I'm fascinated by the idea of us all watching this from our tiny corner of the universe. Let me know in the comments what time it is where you are and whether you're watching this under sunlight or starlight. And if you're ready for the voyage, hitting that like button and subscribing tells me you're on board. In the 1990s, two teams of astronomers began one of the most patient experiments ever attempted. One team used the Keck Observatory in Hawaii, the other used the Very Large Telescope in Chile, both focused on the same tiny patch of sky, the center of the Milky Way. They used infrared cameras, working in wavelengths our eyes can't see, and they began tracking individual stars near Sagittarius A. Not thousands of stars, just a few dozen, year after year, image after image, watching how they moved, and the stars were moving fast. Not the slow drift you'd expect from distant objects. These stars were racing around something unseen, like planets around a star, but far more extreme. Tight orbits, elliptical paths, violent speeds. One star became especially important, a blue-white star. Nothing remarkable about it, except where it was and how it moved. They called it S2, and S2 would change everything. S2 completes an orbit around Sagittarius A every 16 years. That is incredibly fast for something near the center of a galaxy. Our Sun takes about 230 million years to orbit the Milky Way once. S2 does it in 16. At its closest approach, S2 passes within about 17 light-hours of the black hole. For comparison, Neptune is only about 4 light-hours from the Sun. S2 gets that close to a black hole, and at that distance it accelerates to around 2 to 3% the speed of light, roughly 7,000 to 8,000 kilometers per second, fast enough to travel from Earth to the Moon in less than a minute. Scientists followed S2 for decades, tracking its motion year after year. They watched it swing past the black hole in 2002, and again in 2018, one complete 16-year orbit, frame by frame, year by year. They could see it speed up as it approached the black hole, and slow down as it moved away. The evidence was impossible to ignore. Deep within the densely packed core of our galaxy lies Sagittarius A, pronounced Sagittarius A star, an enigmatic object that continues to captivate scientists and astronomers. It is more than just a dot in the sky. It is a profound cosmic phenomenon holding the keys to understanding some of the universe's most profound mysteries. Its significance extends across astrophysics, cosmology, and fundamental physics because it embodies the extreme conditions of gravity, the behavior of matter under intense forces, and the very fabric of space-time itself. Sagittarius A is a supermassive black hole with an estimated mass of about 4 million times that of our Sun. While one of the smaller supermassive black holes, its proximity to Earth makes it especially valuable for study. Located roughly 26,000 light-years away at the galaxy's centre, Sagittarius A is surrounded by a swirling maelstrom of stars, gas, and cosmic dust. This object was once a tantalizing mystery. Astronomers knew something massive lurked at the galaxy's core, but lacked concrete evidence of its nature. Decades of detailed observations using radio and infrared telescopes gradually established that the galactic centre housed a supermassive black hole. Understanding Sagittarius A is crucial because it provides insights into the fundamental physics of black holes, galaxy evolution, and the behaviour of matter under extreme conditions. Black holes are regions where gravity is so intense that nothing, not even light, can escape once crossing the event horizon, the boundary around the black hole. Due to this, direct observation of the black hole itself is impossible. Instead, astronomers infer its properties by examining the effects on its environment, such as the orbits of nearby stars, high-energy radiation from accretion disks, and gravitational influence on surrounding matter. The breakthrough came through tracking the orbits of stars near the galactic centre, especially the so-called S-stars. By monitoring their paths for decades with infrared telescopes, astronomers observed rapid Keplerian orbital motions indicative of a supermassive compact object exerting a formidable gravitational pull. These measurements confirmed that an object of extraordinary mass, several million solar masses, was confined to a very small volume, fitting the profile of a black hole. This evidence solidified the long-held suspicion that Sagittarius A housed the Milky Way's central supermassive black hole. Sagittarius A also serves as a natural laboratory for probing gravity's effects in its most extreme regime. Near the event horizon, the gravitational field is so intense that it tests Einstein's general theory of relativity. A key pursuit for modern astrophysics is to verify whether Einstein's equations hold under these conditions, or if deviation suggests new physics. Precise measurements of star orbits, timing signals from the accretion disk, and gravitational wave detection are vital tools in this quest. Phenomena such as gravitational lensing, where light from background objects is bent by the black hole's gravity, and the behavior of matter spiraling into the accretion disk are important indicators of gravity's behavior under extreme conditions. In 2019, the Event Horizon Telescope, EHT, a global network of synchronized radio telescopes, released the first image of a black hole's shadow, M87s, about 55 million light-years away. Efforts continue to produce a similar image for Sagittarius A, despite challenges posed by the black hole's compactness and dynamic environment. Imaging Sagittarius A enables scientists to see the silhouette of its event horizon against the glowing accretion disk. The size and shape of this shadow encode information about the black hole's mass, spin, and fundamental nature. Comparing observational results with Einstein's predictions allows rigorous tests of our gravitational theories. Any deviations could suggest new physics beyond Einstein's classical framework, perhaps involving quantum gravity or extra dimensions. Consequently, Sagittarius AI is not merely an object of curiosity, but a crucial testing ground for the limits of our physical laws. Furthermore, Sagittarius A is an active, though relatively quiet, powerhouse, emitting powerful radio, infrared, and X-ray jets or flares. These energetic outbursts result from turbulent accretion, when matter spirals inward at near-light speeds, heating up and emitting radiation before crossing the event horizon. Sometimes, the black hole exhibits sudden X-ray and radio flares, linked to violent instabilities in the accretion disk or magnetic reconnection events. Such phenomena provide critical insights into accretion physics and the mechanisms behind energetic jets observed in many galaxies. Studying Sagittarius A also sheds light on the broader relationship between supermassive black holes and galaxy evolution. Almost every large galaxy is thought to harbour a supermassive black hole at its core. Their growth through accretion and mergers influences star formation, galaxy morphology, and the distribution of matter on cosmic scales. In our galaxy, understanding how Sagittarius AI accumulated mass via gas accretion, star capture, or mergers can inform models of galaxy formation across the universe. Black holes and their host galaxies are interconnected in complex ways. Active black holes, such as quasars, generate enormous luminosities that impact their environment, regulating star formation through feedback. Sagittarius A's relative quiescence offers a more detailed view of a black hole's baseline properties, free from the overwhelming activity seen in some active galactic nuclei. Such dormant black holes are believed to be common in the universe, and studying them helps reveal the life cycles of these cosmic giants. An additional reason to study Sagittarius A is its role in understanding the cosmic history of black hole formation. The earliest supermassive black holes, forming within the first billion years after the Big Bang, challenge current theories because of their rapid growth. Investigations of the nearby mature Sagittarius A offer clues about how these objects originate and evolve. Did they begin as smaller black holes from star collapse and grow through mergers and accretion? Or did they form via more exotic processes, such as the direct collapse of massive gas clouds? Insights from Sagittarius A help refine models of early universe structure formation and galaxy emergence. Moreover, Sagittarius A is vital for testing the intersection of gravity and quantum mechanics. Black holes serve as natural sites where known physics, quantum theory, and Einstein's relativity might break down or require unification into a more comprehensive theory of quantum gravity. Observations of the near-horizon zone, where high-energy phenomena occur, are essential to this pursuit. Questions about the nature of the event horizon, Hawking radiation, and the information loss paradox are intrinsically linked to black hole properties like Sagittarius A. From a technological standpoint, efforts to study Sagittarius A skangs have driven advances in observational astronomy and telescope technology. The development of the EHT, for example, has pushed the limits of high-frequency radio imaging and interferometry, enabling measurements at unprecedented resolutions. These innovations have wide-ranging applications, improving fields such as signal processing, optics, and data analysis. The quest to image the black hole shadow exemplifies international cooperation, with scientists pooling resources and expertise to answer fundamental questions. Despite its importance, Sagittarius A remains elusive in many ways. The dense environment around it, filled with interstellar dust and gas, obscures optical observations, requiring reliance on radio, infrared, and X-ray wavelengths capable of penetrating dust clouds. Its emissions are variable and complex, complicating modelling efforts, as the environment is constantly changing. Nevertheless, ongoing observations continually deepen understanding of this cosmic enigma, revealing more about its properties and behaviour. The implications of learning about Sagittarius A extend across astrophysics. Its behaviours and properties influence galaxy formation and evolution. The dynamics of its accretion disks help elucidate how energetic jets and outflows are powered, affecting star formation and galactic structure. Its role as a near-dormant black hole provides a template for understanding the life cycle of supermassive black holes and their impact on cosmic environments. Studying Sagittarius A also informs models of how supermassive black holes formed in the early universe. The challenges posed by the rapid emergence of massive black holes in young galaxies remain unresolved. Insights from Sagittarius A, a mature black hole, offer clues about whether such objects grew from smaller progenitors or formed through more exotic processes, informing theories about the early universe's structure and the rapid growth of cosmic structures in the universe's first billion years. Additionally, Sagittarius A plays a role in understanding the quest for a unified theory that combines gravity with quantum mechanics. Black holes are theorized to be the sites where current physics may falter, providing opportunities to discover phenomena like Hawking radiation, the nature of the event horizon, and the resolution of information paradoxes. Observations in the high-energy environment near Sagittarius A could reveal physical effects that challenge existing theories, driving the development of quantum gravity models. Technological innovations driven by the study of Sagittarius A have broader impacts. The development of the Event Horizon Telescope, for example, has advanced high-frequency radio imaging and interferometry techniques. Such progress enhances capabilities in signal processing, space science, and data handling, benefiting other areas of astronomy and physics. International collaborations and technological advancements created for imaging Sagittarius A exemplify how science pushes the boundaries of what's possible. Despite challenges posed by its environment, such as dust obscuration and variability, researchers persist in studying Sagittarius A's. Infrared and radio observations continue to reveal its secrets, allowing us to refine models despite the complexities. As techniques improve and new instruments come online, understanding of this black hole deepens, steadily unveiling new insights into its physics, environment, and role in the cosmos. The broader implications of understanding Sagittarius A are profound. The behavior and properties of supermassive black holes impact galaxy formation, star formation, and the evolution of the universe. The physics of accretion disks and jets inform models of energetic phenomena across the universe. Testing gravitational theories through observations of Sagittarius A helps refine our understanding of the fundamental laws of nature, and potential deviations from Einstein's predictions could unveil new physics. In summarizing, Sagittarius A exemplifies humankind's curiosity and our capacity to probe the universe's deepest secrets. Its study melds observational astronomy, theoretical physics, and technological innovation. It provides a glimpse into the extreme universe, where gravity distorts space-time, matter exists at limits, and the fundamental fabric of reality becomes a laboratory for discovery. As measurements and techniques improve, Sagittarius A will remain central to unlocking the universe's grand mysteries. Contemplating Sagittarius A also prompts profound philosophical questions about humanity's place in the cosmos. It reveals how cosmic phenomena intertwine with fundamental physics and cosmic history. Unraveling the black hole at our galaxy's core can shed light on galaxy origins, the evolution of cosmic structures, and perhaps the universe's ultimate fate. Its existence urges us to consider the nature of space, time, matter, and energy, expanding human knowledge and imagination. In conclusion, Sagittarius A is far more than a hidden mass. It is a cosmic hub influencing galactic evolution, a natural laboratory for testing physical laws, and a beacon guiding us toward understanding the origins and future of the universe. Scientific efforts worldwide continue to peel back its layers of mystery. Each new observation, model, or technological advance helps deepen our understanding, making Sagittarius A a cornerstone of contemporary astrophysics. It continues to inspire, challenge, and illuminate humanity's quest to comprehend the universe at its most fundamental levels. Sagittarius A exemplifies the ongoing human pursuit of knowledge and our desire to understand the universe's deepest secrets. Its study represents a confluence of scientific disciplines, technological progress, and curiosity-driven exploration. As new data and theories emerge, our comprehension of this black hole and its implications for cosmic evolution grow richer. It reminds us that the universe still holds many mysteries, and through perseverance and innovation, we can continue unveiling its secrets, forging connections across physics, astronomy, and philosophy. By exploring Sagittarius A, scientists gain insights into the formation and growth of black holes, the behavior of matter and gravity under extreme conditions, and the history of our galaxy. It acts as a nearby laboratory to test the predictions of Einstein's relativity and probe the interface between quantum mechanics and gravity. Moreover, its study underscores the importance of international collaboration and technological innovation in tackling some of the most profound questions in science. The ongoing efforts to image Sagittarius A with the Event Horizon Telescope and other instruments symbolize the relentless human drive to understand our cosmic environment. These endeavors challenge us to develop increasingly sophisticated tools, improving imaging resolution, data processing, and theoretical modeling to decipher the black hole's secrets. The technological advancements made in this pursuit have broader implications, benefiting numerous fields beyond astrophysics. Despite the difficulties, the pursuit of understanding Sagittarius A continues with vigor. Its complex, dynamic environment offers a wealth of information, driving advancements in observational astronomy. As telescopes become more powerful and our theoretical models more refined, our picture of this black hole and its role in the cosmos becomes clearer. Each discovery pushes the frontiers of physics and cosmology, and the ongoing investigation into Sagittarius A promises to reveal new truths about the universe's structure and origins. In contemplating Sagittarius AI, we are reminded of the interconnectedness of cosmic phenomena and fundamental physics. The black hole embodies extremes, gravity so intense that it warps space-time, matter compressed to its limits, and energy conditions that challenge our understanding. Its study not only advances scientific knowledge, but also deepens philosophical reflection on our place in the universe, the nature of reality, and the limits of human understanding. Ultimately, Sagittarius A stands as a testament to the enduring human spirit of curiosity and discovery. Its mysteries continue to inspire scientific and philosophical exploration. Through persistent observation, technological innovation, and theoretical insight, we're gradually unveiling the secrets of this cosmic powerhouse. As we do, we gain not only knowledge but also a deeper appreciation for the universe's grandeur and complexity. Knowing more about Sagittarius A helps us understand the universe's past, present, and potential future, enriching our perspective on existence itself. The scientific quest to understand Sagittarius A exemplifies our relentless pursuit of truth and our capacity to probe the universe's deepest secrets. It emphasizes the importance of curiosity, collaboration, and technological progress. As we peer into the heart of our galaxy, we not only learn about a distant black hole, but also about the fundamental laws that govern reality. Each step forward builds a bridge between the known and the unknown, offering hope that the universe's greatest mysteries are within reach. In sum, Sagittarius A is a cornerstone of modern astrophysics, a natural laboratory for testing the laws of physics, and a symbol of human curiosity. Its study offers insights into galaxy formation, black hole physics, and the interplay of gravity and quantum phenomena. As scientific endeavours continue, Sagittarius A will remain central to our efforts to understand the universe's origins, structure, and ultimate fate. This journey of discovery reflects our deepest desire to make sense of the cosmos and our place within it, underscoring the profound connection between exploration and human experience. The ongoing exploration of Sagittarius A reminds us that the universe still holds many secrets. It exemplifies how curiosity-driven science can lead to remarkable technological advances and deepen our understanding of fundamental physics. With each new observation, we draw closer to unlocking the mysteries of space-time, matter, and energy at their most extreme. This pursuit not only advances science, but also enriches human culture and philosophy, inspiring future generations to ask the biggest questions about existence and the cosmos. As we look outward at Sagittarius A, we also look inward, challenging and expanding our understanding of fundamental laws, developing new theories, and pushing the limits of technology. The black hole's enigmatic nature fuels the scientific imagination, prompting new hypotheses, experiments, and collaborations worldwide. In doing so, Sagittarius A continues to serve as a beacon guiding humanity's quest for knowledge, illuminating the dark corners of the universe's grand design, and inspiring the enduring human spirit of discovery. The story of Sagittarius A begins long before astronomers caught its faint signature, glowing in the depths of the cosmos. For decades, the centre of our galaxy remained a mysterious and elusive region, shrouded in dust and gas that masked its secrets from visible light. It was only through pioneering advancements in observational technology that astronomers finally uncovered the presence of what they now know as Sagittarius A, a supermassive black hole lurking silently at the very heart of the Milky Way. In the early 20th century, astronomers puzzled over the motions of stars in the galaxy's central region. Observations indicated that stars in the core, particularly those within a few light years of the centre, exhibited rapid and complex motions. Yet, in visible light, the core remained a dull, obscured patch, ballads of gas, dust, and stellar clouds blocking direct observation. Early telescopes, while powerful for their time, couldn't pierce the dense shroud of cosmic dust or reveal what's hiding behind it. It wasn't until the mid-20th century that astronomers took a giant leap forward with the advent of radio astronomy. Unlike visible light, radio waves can penetrate dust clouds, revealing the hidden universe behind the veils of cosmic grime. The development of large radio dish antennas, such as the Parkes Radio Telescope in Australia, and later interferometers with much higher resolution, provided the tools necessary to explore the galaxy's core in radio frequencies. Yet, discovering a compact, bright source at the centre of the Milky Way in radio wavelengths was just the beginning. The breakthrough came with the refined technology of Very Long Baseline Interferometry, or VLBI. This technique involved combining radio signals from multiple antennas spread across vast distances, effectively creating a virtual telescope the size of the Earth's diameter. VLBI achieved unprecedented angular resolution, allowing astronomers to pinpoint compact radio sources with extraordinary precision. In 1974, a team of astronomers using the new interferometric techniques identified a bright, compact radio source precisely located at the galactic center. This source was named Sagittarius A, due to its position in the constellation Sagittarius. The A distinguished it among other radio sources in the region, but Sagittarius A was initially thought to be a dense cluster of stars or perhaps a supernova remnant, an energetic remnant from a dying star. It was the subsequent observations that turned the tide of understanding. Irregular and rapid variability in Sagittarius A's radio emissions hinted that the source was not a collective of objects, but a single, compact entity. Its flickering nature suggested something energetic and compact, possibly a supermassive black hole. The leap to understanding the true nature of Sagittarius A required even more advanced technology. By the end of the 20th century, astronomers employed Very Long Baseline Array (VLBA) telescopes, a network of 10 antennas across the United States, synchronized to operate as a single colossal instrument. This network facilitated detailed radio imaging of the galactic core, revealing the structure and behavior of Sagittarius A with much higher clarity than ever before. Simultaneously, the development of infrared astronomy played a crucial role. Infrared light, which also penetrates dust, allowed scientists to observe stars moving at dizzying speeds close to the galactic center. Observations with ground-based telescopes equipped with adaptive optics and space-based infrared telescopes, like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, offered stunningly detailed views of stellar orbits near Sagittarius A. The motions of these stars, particularly the star known as S2, pressed the undeniable evidence for a colossal, invisible mass concentrated in a tiny volume. The most compelling proof came from tracking these stars over decades. Their swift orbits, some making complete circuits around the galactic center in as little as 15 years, indicated that the mass lurking there ranged around 4 million times the mass of our Sun, compressed into a radius no larger than our solar system. This dense, massive object matched the predictions for a supermassive black hole. Moreover, the advancements in X-ray and infrared observatories added key pieces to the puzzle. When Sagittarius A occasionally flared in X-ray wavelengths, it suggested material was occasionally being drawn into its gravitational embrace, heating up to millions of degrees and emitting powerful X-rays. These bursts, observed with the Chandra X-ray Observatory, confirmed the presence of a supermassive black hole that sometimes fed on surrounding gas. Infrared and radio telescopes also detected that Sagittarius A was incredibly quiet most of the time, calling attention to its quietude compared to other active galactic nuclei, which shine as luminous quasars when their black holes actively accrete matter. This faint glow is characteristic of a black hole that is less active but nonetheless holds an immense mass. The puzzle pieces came together with a synergy of observational techniques: radio interferometry, infrared astrometry, X-ray monitoring, each technology providing a different perspective on this elusive object. The high-precision measurements of stellar orbits provided conclusive evidence that a supermassive black hole resided at the center of our galaxy. As technology continued to advance into the 21st century, even more sensitive instruments emerged. The Event Horizon Telescope, an unprecedented global network of radio telescopes, aimed to image the event horizon of Sagittarius A. While capturing the black hole's shadow has proven challenging, the very attempt exemplifies how far astronomical technology has come in probing the unseen. In essence, the discovery of Sagittarius A was a triumph of technological ingenuity. It began with the advent of radio astronomy and the implementation of interferometric techniques that allowed astronomers to unveil a point-like radio source at the core of the galaxy. The refinement of these methods, coupled with infrared observations revealing the dynamics of neighbouring stars, ultimately unmasked the invisible yet massive presence lurking at our galaxy's centre. From the first hints of a mysterious radio source in the 1970s to the decades-long campaign of precise measurements and multi-wavelength investigations, the identification of Sagittarius A stands as a testament to humanity's relentless pursuit of understanding. It exemplifies how technological innovation, building bigger telescopes, developing interferometric arrays, and exploiting different wavelengths, can peel back cosmic dust and darkness, revealing the universe's hidden giants. With each advancement, we get closer to understanding the true nature of this invisible behemoth, the engine powering the heart of the Milky Way, and perhaps unlocking the secrets of black holes themselves. Nestled at the very core of our Milky Way galaxy lies a mysterious astronomical object that has long captivated scientists and stargazers alike, known as Sagittarius A. This celestial phenomenon isn't just another point of light in the vastness of space. It is a beacon that sheds light on the fundamental workings of our galaxy and the universe at large. As the gravitational powerhouse anchoring the Milky Way, Sagittarius A holds the key to understanding the intricate dance of stars, gas, and dark matter that shape the very fabric of our cosmic neighborhood. For decades, astronomers have suspected that the center of the Milky Way hosts a supermassive black hole, an object so dense and compact that not even light can escape its grasp. The quest to confirm the existence of such an entity at the heart of our galaxy led to intense observations and groundbreaking discoveries. Sagittarius A emerged as the lead candidate due to its peculiar radio emissions and the way stars orbit around an unseen but incredibly massive object. Through the relentless application of radio and infrared telescopes, cutting-edge tools that can pierce through the dense clouds of gas and dust obscuring the galactic core, scientists have been able to peer into this mysterious realm with extraordinary precision. Why is Sagittarius A so crucial? Because understanding its properties provides critical insights into the behavior of supermassive black holes, objects that are not only common at the centers of many galaxies, but also play a pivotal role in shaping their evolution. The mass of Sagittarius A is estimated to be about 4 million times that of our Sun. This immense concentration of mass makes it a prime example for studying how gravity shapes the environment in the core of a galaxy. Every star that orbits this invisible giant tells a story about the gravitational forces at play, allowing researchers to test predictions made by Einstein's theory of general relativity under conditions impossible to replicate on Earth. These stellar orbits are not just fascinating to observe, they are vital clues that help astronomers measure the black hole's size and mass with incredible accuracy. When stars whiz past close to Sagittarius A, their rapid velocities and changing positions serve as cosmic probes. By tracking these motions over decades, astronomers have been able to map the gravitational well created by Sagittarius A, confirming its supermassive nature firmly beyond any doubt. This level of detail has transformed our understanding of such objects from speculative supposition to well-established fact. Moreover, Sagittarius A is a natural laboratory for exploring how black holes influence their environments. Though often associated with destruction and cosmic chaos, supermassive black holes also have a symbiotic relationship with their host galaxies. The activity in Sagittarius A, including occasional bursts of high-energy radiation, helps scientists understand the feedback mechanisms that regulate star formation and galactic growth. These black holes can serve as cosmic engines, periodically ejecting material at near-light speeds, influencing the distribution of gas and dust in the galactic core. By analysing these emissions, researchers decipher the processes that fuel black hole growth and the ways in which their energetic outputs can either quench or promote star formation. Understanding Sagittarius A also helps answer deeper questions about the life cycle of galaxies. Is our galaxy destined to harbour a supermassive black hole forever? How do such massive objects form in the first place? Do they grow primarily by swallowing matter, or do they form from the mergers of smaller black holes over millions of years? The answers to these questions connect not only to the history of the Milky Way, but also to the evolution of galaxies across the universe. Observing Sagittarius A provides a nearby example of the extreme environments that big black holes create, offering a window into the processes that shaped the early universe when galaxies were forming and evolving more rapidly. Furthermore, Sagittarius A acts as a testing ground for the limits of physics itself. The environment around a supermassive black hole is an extreme universe unto itself, with intense gravitational fields, accretion disks of superheated material swirling at relativistic speeds, and potent magnetic fields. Studying how matter behaves in this setting helps physicists refine their understanding of gravity, quantum mechanics, and the nature of space-time. Observations of events such as star or gas infalls into Sagittarius A allow scientists to observe phenomena that challenge and extend current theories, inching us closer to a more complete unified understanding of the fundamental forces of nature. In the grand scheme of cosmic exploration, Sagittarius A serves as both a lighthouse and a laboratory. Its study illuminates the unseen, revealing how supermassive black holes form, grow, and influence their surroundings. By unraveling the secrets of this invisible giant, scientists are piecing together a more comprehensive picture of the Milky Way's history and evolution. Each new discovery about Sagittarius A reminds us that even in the darkness, there is knowledge waiting to be uncovered. Knowledge that has the power to tell us who we are and where we come from in this vast universe. So, in the quest to understand our galactic home, Sagittarius A stands as an essential anchor, an invisible giant that whispers the stories of cosmic forces at play. Its role in our understanding of the Milky Way is unparalleled, acting as a cosmic Rosetta Stone for unlocking the mysteries of supermassive black holes, galactic dynamics, and the fundamental laws that govern everything from the smallest particles to the largest structures in the universe. Through its study, we gain not only insight into the heart of the galaxy, but also a deeper appreciation of the complex, interconnected universe we inhabit. Deep within the heart of our galaxy lies a mysterious behemoth that remains largely unseen, an object so massive and elusive that it earns the nickname, the Invisible Giant. This name doesn't come from a lack of size or power, but from the profound difficulty in observing it directly. To understand why this supermassive object is called the Invisible Giant, we need to explore the environment that cloaks it in secrecy. Imagine standing in a bustling city surrounded by thick fog, skyscrapers, and busy streets. Trying to spot a single individual amid all that chaos would be very difficult. That's similar to the challenge astronomers face when trying to observe Sagittarius A, the supermassive black hole at our galaxy's core. It's hidden behind layers of dust, gas, and dense stars, which absorb, scatter, and obscure signals that could reveal its presence. Black holes don't shine by themselves. Their defining feature is the event horizon, the point of no return, beyond which nothing, not even light, can escape. Because of this, black holes are intrinsically invisible. Looking directly at Sagittarius A, it appears as a dark, starless region, amid the glowing stars and interstellar matter. But the story isn't only about their invisibility, it's about what happens around them. Despite being unseen, astronomers suspected something lurked there long before they could observe it directly. The key was studying the motion of stars orbiting the galactic center. These stars move at incredible speeds, much faster than stars elsewhere in the galaxy. According to Newtonian physics and Einstein's general relativity, such rapid orbits suggest a massive object in a very small region, more mass than could be contained in stars or visible matter alone. This evidence points toward a supermassive black hole, millions to billions of times the Sun's mass packed into a region no larger than our solar system. Yet, even with such strong evidence, the black hole itself remains unseen. The invisible part of its name stems from its inability to emit or reflect detectable light. Much of what we know about Sagittarius A comes from indirect observations. By carefully monitoring stars flickering and dance around the galactic center, astronomers piece together a picture of a colossal gravity well. These stars act as test particles, their paths bending and accelerating under the black hole's tremendous gravitational pull. When a star passes closely, its orbit shifts, and astronomers detect Doppler shifts in the light, revealing their speeds and the mass of the hidden object. Another way to infer the black hole's presence is through high-energy phenomena like X-ray emissions. Occasionally, gas and dust are caught in the black hole's gravitational pull, heating up to millions of degrees and emitting X-rays before crossing the event horizon. These signals are fleeting and faint, often drowned out by brighter sources, making their detection challenging. Recent technology, like very long baseline interferometry, has allowed astronomers to produce the first direct images of the region around Sagittarius A. The Event Horizon Telescope, a global network of radio telescopes working together, captured a faint shadow of the event horizon against the bright accretion disk. However, even this amazing image only hints at the black hole's silhouette. The black hole itself remains fundamentally invisible, an abyss hiding in plain sight. Ultimately, the reason Sagittarius A is called the Invisible Giant isn't just because it's elusive, it also highlights the ingenuity needed to deduce its existence. It reminds us that some of the universe's most powerful objects reveal themselves indirectly, by shaping their surroundings in subtle, awe-inspiring ways. Its shadow and the stellar dance around it tell a story of gravitational influence so strong it warps spacetime itself. Yet the black hole remains hidden, a giant lurking at the galaxy's centre, unseen but undeniably impactful. Astronomers have developed a suite of ingenious techniques to study objects that remain hidden from direct observation, and nowhere is this more apparent than in their quest to understand the supermassive black hole lurking at the very heart of our galaxy, Sagittarius A. These enigmatic giants are cloaked in darkness, their event horizons preventing any light from escaping, making them invisible to traditional telescopes. Yet, through a combination of clever methods, astronomers have managed to piece together a detailed picture of their nature and behaviour. One of the most fundamental tools in this endeavour is the study of indirect signals, traces left by the object's gravitational influences and the light that interacts with their surroundings. Although Sagittarius A itself emits little to no detectable light, the environment around it is a bustling cosmic city, filled with stars, gas and dust. These objects dance and shimmer under the influence of the black hole's immense gravitational pull, providing clues that can be deciphered through careful observation. For instance, astronomers monitor the motion of stars orbiting close to the galactic centre with high-precision instruments. By tracking their paths over many years, they observe stars zigzagging through space at astonishing speeds, some whirling around the invisible giant at velocities that can reach several thousands of miles per second. The only way to explain such rapid and tightly bound orbits is if a massive, compact object resides at the centre. Calculations of the star's orbital parameters reveal that this unseen mass must be about 4 million times that of our Sun, compressed into a region no larger than our solar system. This remarkable measurement provides strong evidence for the existence of Sagittarius A being a supermassive black hole. Another technique involves examining the light from material accreting or falling into the black hole. As gas and dust spiral inward, they heat up and emit X-rays and radio waves before crossing the event horizon. Although the black hole itself doesn't shine, the energetic process of accretion produces telltale electromagnetic signals. Telescopes tuned to X-ray and radio wavelengths detect bursts, flares and constant emissions that act as signatures of the black hole's feeding frenzy. These observations not only confirm the presence of a supermassive object, but also help characterize its properties, such as mass, spin, and how it interacts with the surrounding environment. Sometimes, astronomers observe the effects of a black hole's gravity on distant light sources. This includes gravitational lensing, where the intense gravity bends and distorts the paths of background light. Although such lensing is easier to see in more distant, massive galaxy clusters, careful analysis can sometimes reveal subtle distortions near our galactic centre, offering another way to probe the black hole's gravitational field. Additionally, technology advances have enabled astronomers to employ interferometry, a technique that combines signals from multiple telescopes spread across vast distances to mimic a much larger instrument. The Event Horizon Telescope, a global network of radio dishes, has achieved the unprecedented feat of capturing the shadow of Sagittarius A's event horizon. While this image does not see the black hole directly, it reveals the silhouette of the event horizon against the glowing backdrop of infalling material. This critical data corroborates theoretical models and provides visual evidence of the black hole's existence. In some cases, astronomers draw on computer simulations that incorporate the physics of general relativity and astrophysics to interpret what they observe. These models predict how matter behaves as it approaches a black hole, what signatures it should produce, and how light should be bent and emitted. When observational data matches these predictions, confidence in the black hole's properties grows. The study of objects like Sagittarius A exemplifies the creative spirit of astronomy. In reliance on indirect evidence, the field transforms faint whispers, ripples in light, star movements, and the shadows cast by invisible giants into a profound understanding of phenomena that are otherwise forever cloaked in darkness. It's a testament to human ingenuity. Even when the object itself refuses to be seen, its existence can be inferred, its secrets revealed, and its nature understood through a symphony of clever observations, physics, and technological innovation. The story of our galaxy, the Milky Way, spans billions of years, marked by cosmic collisions, gradual growth, and the emergence of its central powerhouse. To understand the supermassive black hole Sagittarius A, we should trace the galaxy's origins, how it formed, how its core evolved, and how this history connects to the universe itself. It all begins shortly after the Big Bang, about 8 billion years ago. The universe was a hot, dense soup of particles, cooling as expansion spread cosmic fabric apart. Tiny density fluctuations in primordial gas and dark matter started to grow under gravity. Small regions of higher density attracted surrounding matter, forming seed structures that would become galaxies. Over millions of years, these seed regions coalesced into dwarf galaxies, mini-galaxies within dark matter filaments. These systems grew through mergers and accretion, pulling in gas, stars, and dark matter over cosmic time. Some dwarf galaxies merged with larger structures, contributing to the formation of the Milky Way. Initially, the early Milky Way was chaotic. Its first stars ignited in dense gas clumps, fueling rapid star formation. Massive, short-lived stars exploded as supernovae, enriching the surrounding gas with heavier elements, laying the chemical foundation for subsequent star generations. This tumultuous activity shaped the galaxy's initial structure, setting the stage for ongoing evolution. As it grew, the galaxy developed more defined features: spiral arms, a central bulge, and an extensive halo of stars and dark matter. The formation of the galactic core was crucial. Dense gas and star clouds collapsed further, funneling material inward. The core became a hub of star formation, dense clusters, and complex gravitational interactions, eventually giving rise to the supermassive black hole that resides there today. How did such an enormous black hole form? Did it start as a massive star collapsing into a black hole, later fed by surrounding matter? Or did it emerge from the direct collapse of dense gas clouds early in galaxy formation? Scientific models suggest both pathways, but evidence favours an early seed black hole forming within the first billion years after the universe's birth. This seed then grew over time through accretion, pulling in gas and stars, and mergers with other black holes. Early universe mergers were frequent, as galactic collisions and interactions happened often. When two galaxies merged, their central black holes spiraled inward through gravitational waves until they merged into a more massive black hole. Each merger contributed to the central black hole's growth, fueling its supermassive status. In the Milky Way, this process took billions of years. Sagittarius A grew from a modest seed black hole to its current mass of about 4 million times that of the Sun through accretion and mergers. Later mergers, especially with satellite galaxies like the Sagittarius dwarf galaxy, continue to influence its evolution, sometimes triggering starbursts and feeding material towards Sagittarius A. Amid this turmoil of galactic growth and starbirth, the core became a bustling environment. Dense molecular clouds, star clusters, and stars orbiting close to the centre contributed to its dynamic activity. Over billions of years, the environment and the gravitational influence of Sagittarius A shaped the orbits and properties of nearby stars, such as the recently observed S-stars that zip around the black hole at incredible speeds. The evolution of the galactic core isn't just about feeding the black hole, it's also about how stars and gas interactions shape the galaxy's history. During active periods, gas clouds collapsed inward, fueling Sagittarius A's and powering phenomena like X-ray flares. Quieter phases followed, with less material falling inward, leaving the black hole relatively dormant. The shape and features of the Milky Way's core reflect both chaos and calm. Early on, it was likely more active, with frequent collisions and gas inflows. Over time, as the galaxy settled into a spiral form, the core stabilized, although remnants of past mergers, streams of stars and remnants of smaller galaxies are visible today, telling tales of cosmic interactions. Today, astronomers study the stars near Sagittarius A to unravel this history. By measuring their motions, compositions, and orbits, they piece together the galaxy's growth and the black hole's feeding history. Stellar surveys show periods of rapid black hole growth, especially during early epochs, punctuated by quieter times. Each event paints part of the grand galaxy formation story. The story of our galaxy is ongoing and constantly refined, with new observations from telescopes and space missions. The legacy of ancient mergers and star formation episodes is embedded in the galaxy's structure. Looking into the galaxy's core, we see not only a supermassive black hole, but also the record of billions of years of cosmic evolution, a reflection of a dynamic, ever-changing universe. Understanding this history offers insights into galaxy formation across the cosmos, the Milky Way's formation of its core, growth from seed black holes, and past mergers, echo processes occurring in countless galaxies. Our galaxy's early days set the stage for its present form, a sprawling, complex structure with a hidden giant at its center. The transformation from primordial chaos to galactic order is one of the universe's grand narratives, with Sagittarius A serving as a silent sentinel, reminding us of the cosmic forces crafting worlds, stars, and galaxies. The formation of supermassive black holes like Sagittarius A remains one of the greatest mysteries in cosmology. Their origins are intertwined with galaxy formation, spanning billions of years filled with dramatic events, rapid growth, and complex processes. To understand their origins, we explore the universe's early epochs, just hundreds of millions of years after the Big Bang, when primordial gas clouds, stars, and galaxy seeds emerged. The key question is how such colossal objects, exceeding millions or billions of solar masses, formed so quickly. One prominent theory involves stellar remnants. In the universe's infancy, massive stars formed from dense gas. These stars burned brightly and short-lived, exploding as supernovae after a few million years, leaving behind neutron stars and stellar mass black holes. Gravitational attraction caused these remnants to sink toward proto-galaxy centers. Over time, through hierarchical merging and accretion, these dense remnants could collide and coalesce into more massive black hole seeds. Envision a dense city of remnants, black holes and neutron stars, merging and colliding. As the galaxy's core evolved, these objects could combine, forming a seed black hole. This seed then grew by accreting surrounding gas and stars, each addition increasing its mass. Black hole growth via accretion is especially efficient in gas-rich early environments, facilitating rapid mass increases. Another leading idea is direct collapse. Under specific conditions, massive gas clouds, trillions of times the Sun's mass, could undergo rapid direct collapse into black holes. These direct collapse black holes would serve as large seed black holes, much bigger than stellar remnants, forming swiftly in the early universe. Conditions favoring this include rapid gas inflow, suppression of star formation to prevent fragmentation, and low metal content, which inhibits cooling and star formation. This process could produce seed black holes roughly 100,000 times the Sun's mass, providing a head start for fast growth. From these large seeds, subsequent growth through accretion could produce supermassive black holes within a few 100 million years. High redshift quasars, bright active galactic nuclei powered by accreting black holes, provide evidence of such rapid formation. Some quasars host black holes exceeding 1 billion solar masses, aligning with models that require swift early growth. Their existence suggests supermassive black holes can form quickly enough to match observations. Galaxy mergers also contribute to black hole growth. Galaxies frequently collide and merge, bringing their central black holes into proximity. Over time, these black holes form binaries, gradually spiraling inward through gravitational interactions with stars and gas. Eventually, they merge into a more massive black hole, amplifying the galaxy's core growth. This cosmic dance links galaxy evolution closely to black hole development over cosmic time. In addition to mergers, black holes grow by consuming vast amounts of gas. In the early universe's dense environment, cold gas streams inward toward galactic centers, forming a supermassive accretion disk, an elaborate whirlpool of material. Turbulent processes within this disk generate high-energy radiation, illuminating the galaxy's nucleus as a quasar or active galactic nucleus. These luminous phases, characterized by intense radiation, regulate black hole growth, feedback mechanisms that heat and disperse surrounding gas, preventing unchecked growth. Recent theories propose stellar clusters as black hole nurseries. Dense cluster cores can undergo catastrophic core collapse, forming black holes that serve as seeds for later supermassive black holes. If this process operates efficiently, it might explain how black holes grow to enormous sizes within relatively short cosmic periods, complementing other formation scenarios. The relationship between black holes and their host galaxies emphasizes coevolution. Observations reveal a tight correlation, the M-sigma relation, between black hole mass and properties of the galaxy's bulge, such as mass and velocity dispersion. This suggests black holes and galaxies grow together, shaping each other's evolution. As galaxies assemble through star formation and mergers, their central black holes similarly accumulate mass, linking their growth closely. Throughout cosmic history, the paths of supermassive black holes and their host galaxies are interconnected. However, important questions remain. For example, how did the earliest black hole seeds form in the universe's first few 100 million years? Was it predominantly through direct gas cloud collapse, stellar remnant mergers, or a combination? Many models suggest multiple pathways contributed, but the exact processes are still under investigation. The discovery of intermediate mass black holes, with masses between 1,000 and 100,000 solar masses, offers clues. These objects could represent a transitional phase, bridging stellar mass and supermassive black holes. Studying them could reveal dominant growth processes and help explain how supermassive black holes reach their large sizes in a short cosmic time. Progress continues with advanced telescopes and simulations. Future missions aim to peer deeper into the early universe, seeking the initial moments of black hole formation. Understanding these origins may clarify whether rapid gas infall, chaotic mergers, or other processes primarily drove their growth. Many questions persist, but ongoing research and technological advancements promise to shed light on this mystery. The tight link between black holes and their galaxies supports the idea of mutual influence. Feedback from active black holes can regulate star formation in host galaxies, and vice versa. This interplay shapes galaxy evolution, with black hole growth often peaking during periods of galaxy assembly, such as galaxy mergers or intense starbursts. Despite significant progress, many details remain elusive. For example, how common were different formation pathways early in the universe? Were some black holes born large through direct collapse, while others grew gradually from stellar remnants? Perhaps both processes contributed, with their relative importance varying across cosmic time. The study of intermediate mass black holes is promising. By identifying and analysing these objects, astronomers can uncover clues about black hole growth pathways, initial properties, and environmental influences. This understanding will help determine whether the dominant mode of supermassive black hole formation involved direct collapse, stellar remnants, or combinations. Future telescopes, such as the James Webb Space Telescope, aim to observe the universe's earliest galaxies and black holes. Simulations of galaxy and black hole coevolution will become more sophisticated, providing detailed predictions for comparison with observations. These tools will deepen our understanding of the processes that gave rise to objects like Sagittarius A. As knowledge advances, the picture of black hole origins will become clearer. Researchers will better understand how initial seeds, whether from gas cloud collapse or stellar remnants, grew through accretion and mergers, shaping the universe observed today. These insights will have broad implications across astrophysics, cosmology, and fundamental physics. In summary, the formation of supermassive black holes involves multiple interconnected processes: stellar remnants, direct collapse, galaxy mergers, gas accretion, and environmental interactions. Each pathway contributes to black hole growth, with their roles evolving over cosmic time. The combined effects of these mechanisms allowed black holes to reach enormous sizes early in the universe's history, exemplified by quasars and the black hole in our galaxy's centre. The story of Sagittarius A exemplifies this complex narrative. Its existence reflects violent beginnings, rapid growth, and dynamic interactions, evidence of a universe driven by chaotic, powerful forces. Unraveling its origins offers crucial insights into galaxy evolution, black hole physics, and cosmic history. The ongoing quest promises new discoveries that will illuminate the dawn of supermassive black holes and their critical role in shaping our cosmos. The understanding of supermassive black hole origins profoundly influences our comprehension of galaxy formation, the evolution of cosmic structures, and the physical laws under extreme conditions. Studying these objects sheds light on how the universe's largest gravitational wells form and grow, providing a window into fundamental physics. Their rapid assembly and cosmic dawn challenges models and motivates new theories. Currently, scientists consider multiple plausible pathways: direct collapse of massive gas clouds, hierarchical merging of stellar remnants, and growth through gas accretion and galaxy mergers all likely played roles. The relative importance of these processes may vary across different environments and epochs, influencing the diversity of observed black hole masses. Research into intermediate mass black holes might reveal key transitional stages. These objects could be remnants of early phase evolution, providing insights into initial seed properties, environmental effects, and growth mechanisms. Their study helps clarify the link between stellar mass and supermassive black holes. Next-generation telescopes are designed to push observational boundaries, searching for the earliest signatures of black hole seeds. Simulations will refine our understanding of their formation conditions, growth rates, and interactions with their host galaxies. These efforts aim to answer whether rapid gas inflow, violent mergers, or other phenomena primarily formed supermassive black holes. Understanding black hole origins is central to cosmic evolution. Black holes influence star formation, gas dynamics, and galaxy morphology through feedback processes. Their growth rates correlate with host galaxy properties, indicating a coevolution that shapes the large-scale structure of the universe. Despite progress, many questions remain. How did the earliest black holes form? What environmental conditions favored certain pathways? How did the most massive black holes grow so rapidly? These questions motivate ongoing and future research, which will integrate observational, theoretical, and computational approaches. The discovery of intermediate mass black holes provides a promising avenue. By studying their properties and distribution, scientists aim to constrain black hole formation models, identify dominant pathways, and understand implications for cosmic structure formation. These objects serve as key links bridging the known properties of stellar mass and supermassive black holes. In the coming years, advanced observational facilities and simulations will likely illuminate the details of black hole formation. This will help confirm whether direct collapse, mergers, accretion, or a combination of processes was most influential. Such knowledge will refine our understanding of galaxy formation and evolution, informing broader cosmological theories. Ultimately, uncovering the origins of supermassive black holes is essential to understanding the universe. Their evolution reflects the complex interplay of physics, cosmic environment, and galaxy assembly. As our understanding deepens, it will unlock new questions about the nature of gravity, matter, and the early universe, driving forward the frontiers of astrophysics. The case of Sagittarius A exemplifies these processes in action. Its presence at our galaxy's core offers tangible evidence of violent beginnings and rapid growth. Understanding how it formed informs models of galaxy evolution and the physics of black hole growth under extreme conditions, offering vital clues to cosmic history. The quest to explain supermassive black hole origins continues to challenge and inspire scientific inquiry. As models improve and observations become more precise, the picture will become clearer, revealing whether rapid gas inflow, chaotic mergers, or stellar processes were most influential. These insights will integrate into a comprehensive model of cosmic structure formation. In conclusion, multiple mechanisms, direct collapse, stellar remnants, galaxy mergers, and accretion, likely contributed to supermassive black hole growth over cosmic time. Their interplay explains how enormous black holes formed early, shaping galaxy evolution and cosmic history. The story of Sagittarius A embodies this complex process, illustrating the violent, dynamic universe that gave rise to these giants. The relationship between Sagittarius A and the evolution of the Milky Way is profound, shaping the galaxy over billions of years by illustrating how a black hole's appetite can influence its entire structure. At first glance, the supermassive black hole at the galaxy's center may seem passive, an invisible anchor pulling everything inward. But in reality, it plays a dynamic role, fueling growth, influencing structure, and orchestrating the cosmic dance of the Milky Way. In the early universe, galaxies were just beginning to form from swirling clouds of gas and dark matter. The seeds of Sagittarius A likely originated from dense gas cloud collapses or merging smaller black holes. Over cosmic time, as stars formed and expired, much of the galactic gas and dust was funneled inward, feeding the black hole. This process sparked periods of intense activity called active galactic nuclei, where the black hole's accretion disk radiated so brightly it outshone entire galaxies for millions of years. Today, the Milky Way appears quieter, but Sagittarius A has not always been subdued. The feedback loop between the black hole and galactic gas is critical. When Sagittarius A consumes matter, it grows and influences surroundings via jets and radiation emission. These energetic outputs can heat nearby gas, prevent it from cooling, and suppress or trigger star formation. Sagittarius A acts as a cosmic thermostat, sometimes hindering stellar birth, other times facilitating it by compressing gas clouds nearby. Over billions of years, these interactions have shaped the star distribution and overall galaxy morphology. Sagittarius A's gravity also governs the orbits of stars near the centre. Stars moving at thousands of kilometers per second serve as test particles, revealing the black hole's mass and influence over galactic evolution. As these stars age and die, their motions reflect the gravitational well established by Sagittarius A, impacting the galaxy's structure. Their complex dance influences and is influenced by the black hole, a reciprocal relationship driving ongoing evolution. Furthermore, the black hole influences the galaxy's shape. Its gravitational pull anchors the dense central bulge, the star-rich nucleus at the galaxy's core. The size and density of this bulge affect the characteristics of the spiral arms and the galaxy's classification. As the galaxy grows through mergers or gas accretion, Sagittarius A also grows, sometimes swallowing incoming material or being gravitationally perturbed. Such episodes can trigger activity at the core, shaping the galaxy's evolutionary path. Galactic mergers, cosmic collisions over billions of years, highlight Sagittarius A's role in galaxy evolution. When a smaller galaxy merges with the Milky Way, its core can pass near Sagittarius A, bringing new material and temporarily fueling the black hole. These influxes can cause bursts of activity, adding to the black hole's mass and affecting nearby stars' orbits. Such events can shuffle the galaxy's halo and flip its spin, influencing its ultimate structure. Sagittarius A also acts as a cosmic chronicle, preserving clues of the galaxy's past interactions and growth. Variations in its activity, inferred from accretion history, reveal the Milky Way's formative events. Observations of X-ray relics and radio emissions act as echoes of past feeding bursts, illustrating a turbulent history marked by mergers and growth phases. These signals weave a narrative of an evolving galaxy, with the black hole as both participant and witness. The galactic environment around Sagittarius A is shaped by the black hole's gravity. Gas streams and dense star clusters near the core are influenced by its pull, affecting their formation and evolution. Sometimes, gas spirals inward, forming accretion disks that feed Sagittarius A or is ejected as jets extending into the halo. These phenomena impact local star formation and influence the large-scale structure of the galactic core. The Milky Way's future remains linked to Sagittarius A. As the galaxy drifts through space, ongoing interactions with neighbouring galaxies and intergalactic gas will influence its growth. The black hole will continue to accrete material and produce energetic feedback, shaping its environment. When the Milky Way merges with Andromeda in several billion years, the fate of Sagittarius A will be dramatic, likely experiencing renewed activity. The resulting merger could lead to a new galaxy, perhaps a giant elliptical, with the black hole once again dominating as the central gravity well. Despite being invisible to the naked eye, Sagittarius A is the galaxy's heartbeat, a silent master orchestrating its past, present and future. Its gravitational influence governs star formation, morphology and dynamic central evolution. Its activity leaves traces in star orbits, gas clouds and occasional jets, affecting the galaxy's environment over cosmic timescales. The Milky Way story is incomplete without understanding Sagittarius A. It acts both as a bystander and a participant, shaping and responding to the galaxy's growth and changes. Every star, gas cloud and radiation ripple near the core bears its influence. Over billions of years, Sagittarius A's evolution underscores a simple truth. In the cosmic fabric, the unseen often leaves the deepest impact. Absolutely, the universe teems with supermassive black holes like Sagittarius A at the centre of our Milky Way. Far from being unique, these colossal objects are features of large, luminous galaxies across the cosmos. They serve as gravitational anchors, holding galaxies together, with influence extending well beyond their immediate surroundings. Over recent decades, observations have shown that nearly every large galaxy hosts a supermassive black hole, proof of their ubiquity and importance in cosmic evolution. Supermassive black holes generally range from millions to billions of times the Sun's mass. They are distinct from stellar mass black holes, which originate from collapsed massive stars. Their origins and growth mechanisms are still studied. Naturally, one asks, how common are these giants? The answer, very common in large galaxies. Advanced telescopes across the electromagnetic spectrum, radio, optical, infrared, X-ray, find consistent evidence for supermassive black holes at galactic centers. Take the galaxy M87, about 55 million light-years away in the Virgo cluster. Its supermassive black hole, roughly 6.5 billion solar masses, is extensively studied. It features a prominent jet of relativistic particles from the vicinity of the event horizon. The Event Horizon Telescope, EHT, which produced the first direct image of a black hole's shadow in M87 in 2019, confirmed the black hole's presence. The image shows a luminous plasma ring surrounding a dark region, the event horizon's silhouette affirming Einstein's general relativity. This achievement marked a milestone in black hole astrophysics. Similarly, NGC 4258, or Messier 106, provides insights into black hole properties via water mazes orbiting near the nucleus. Precise measurements of maser velocities show that its central black hole has nearly 70 million solar masses, confirming black hole mass estimates independently. Such detailed data shed light on accretion, the process by which black holes gather matter, and feedback, which influences galaxy evolution. Our neighbour Andromeda, M31, about 2.5 million light-years away, hosts a supermassive black hole estimated at 150 million solar masses. Though less active, the black hole's presence is inferred from stellar motions in the core. The fact that even our closest large galaxy has a supermassive black hole supports the idea that these giants are typical in large spirals. Why do some galaxies have larger black holes? Their growth is tightly linked to the evolution of their host galaxies. Galaxies grow through mergers and gas accretion. During mergers, central black holes from colliding galaxies can sink towards the nucleus and coalesce into a more massive black hole. This hierarchical process results in some black holes reaching billions of solar masses. Moreover, the relationship between black hole mass and properties like bulge mass or stellar velocity dispersion suggests coevolution. Empirical correlations, such as the MS relation, show black hole and galaxy growth are interconnected. Feedback mechanisms, including jets and radiation from accretion, can heat or expel gas, regulating star formation. These interactions form a complex dance. Black holes grow within and influence their host galaxies. Many galactic centers house actively accreting black holes, producing luminous active galactic nuclei, AGN. These include quasars, the universe's most energetic objects. Quasars shine brightly due to matter falling in and releasing enormous energy, sometimes outshining entire galaxies. During the early universe's quasar epoch, as 10 billion years ago, such activity was more common, illuminating cosmic history. Today, most black holes are dormant or less active, but remnants of past activity are detectable. Black holes profoundly impact galaxy evolution through feedback. Jets launched from the black hole can extend thousands of light-years and sweep through the galaxy. These jets can expel gas from central regions, suppressing star formation, a phenomenon called radiative or mechanical feedback. Feedback is vital in preventing galaxies from becoming overly massive, and it features prominently in modern galaxy formation models. The study of these black holes continues with new telescopes like the James Webb Space Telescope, which promises to deepen understanding. Early data hint at intermediate mass black holes, ranging from hundreds of thousands to a few million solar masses, that could bridge stellar mass and supermassive black holes. Their formation pathways are debated. Some suggest direct collapse of massive gas clouds, others propose growth from mergers of smaller black holes or stellar remnants. The early universe offers clues about seed black holes. Observations suggest some black holes grew rapidly soon after the Big Bang, posing challenges to formation models. Explaining how they amass such mass within a few hundred million years remains a fundamental puzzle in astrophysics. In sum, supermassive black holes are widespread and key to galaxy structure and evolution. Their gravitational influence, jets, and feedback processes shape cosmic structures on enormous scales. Many questions remain, but ongoing research continually reveals their profound role in the universe's grand design. Looking up at the night sky, it's clear that countless galaxies harbour these invisible giants, powerful, mysterious, and essential to understanding the cosmos's past, present, and future. Their study unites astrophysics in seeking to unravel fundamental mechanisms governing galaxy formation, gravity, and space-time itself. Black holes like Sagittarius A are not merely cosmic curiosities, they are essential pieces of the cosmic puzzle, connecting galaxy evolution with the fabric of space-time and the universe's origins. The story of Sagittarius A's growth over billions of years is a fascinating narrative drawn from observational clues and theoretical insights. Unlike most objects, A supermassive black hole's history isn't stored in a single snapshot. Instead, astronomers reconstruct its past by examining the environment around it, the distribution of stars, gas, dust, and the light travelling across space for millions or billions of years. These clues collectively support our understanding of how Sagittarius A evolved from a small seed into its current colossal form. One compelling piece of evidence comes from stars near the galactic centre. Observations show a dense cluster orbiting very close to Sagittarius A, moving at incredible speeds. The trajectories of these stars resemble a cosmic dance founded on the gravitational influence of a supermassive black hole. By tracking these orbits for decades, astronomers have precisely calculated the black hole's mass, about 4 million times that of the Sun. This immense mass confined within a small volume confirms it is a supermassive black hole rather than a cluster of stars. These stellar orbits also hint at Sagittarius A's growth history. Many of these stars are relatively young compared to the galaxy's age, yet packed tightly near the black hole. This suggests that, over cosmic time, gas and stellar material have funneled toward the centre, feeding the black hole and increasing its mass. This process is akin to the black hole constantly devouring surrounding matter, gradually growing larger. The orbital configurations of these stars serve as a record of the black hole's feeding habits over billions of years. The presence of glowing gas and dust near Sagittarius A further supports its growth story. While the black hole itself is invisible, the material spiralling into it heats up, emitting X-ray or infrared radiation. Periodically, astronomers observe bright flares, sudden, intense bursts of high-energy light. These outbursts evidence episodic accretion events, where gas clouds or star clusters get shredded and swallowed by the black hole. The frequency and intensity of these flares help infer the black hole's mass accumulation rate over time. When observed over different periods, these flares suggest phases of rapid growth, perhaps triggered by large gas clouds or mergers with smaller black holes from satellite galaxies. In the wider context of galaxy evolution, supermassive black holes grow together with their host galaxies. Cosmological simulations grounded in physics and observations suggest that early in the universe's history, seed black holes formed from the remnants of first stars or direct gas collapse. Over billions of years, these seeds merged and accreted matter, evolving into the supermassive black holes we observe today, like Sagittarius A. Models also predict that during quasar phases early in cosmic history, black holes grew at extraordinary rates, sometimes swallowing mass at 1,000 times their current rate. Support for this scenario is strengthened by the detection of intermediate mass black holes in some galaxies, which might be remnants or building blocks of modern supermassive black holes. These smaller black holes can merge and gather matter over cosmic timescales, eventually growing into giants like Sagittarius A. Their existence in smaller galaxies offers a glimpse into the incremental process of black hole growth. Comparing their properties and environments to Sagittarius A's provides insights into the evolutionary pathway. Supermassive black holes are the culmination of countless mergers and accretion episodes dating back to the universe's earliest days. Furthermore, relics and faint signals in the galactic centre support a history of growth. The presence of stellar remnants, such as neutron stars or white dwarfs, around Sagittarius A indicates dynamic past interactions. SMBHs influence their surroundings by capturing or scattering stars and objects. These interactions leave behind signatures like dense populations of old stars or gravitational scars on stellar orbits, offering indirect evidence of the black hole's long-term accumulation. On larger scales, the relationship between Sagittarius A and the Milky Way supports its growth narrative. The galaxy's bulge, the central stellar-rich region, shows signs of coevolution with the black hole. More massive black holes tend to reside in larger, more mature bulges, suggesting a mutual influence over billions of years. Events like galaxy mergers and cosmic gas inflows are believed to have fed the black hole and shaped the galactic core, reinforcing this connection. All these pieces, stellar orbits, gas dynamics, flaring activity, galactic structure, and cosmological models, collectively form a comprehensive picture of Sagittarius A's growth. It's a story of small beginnings, steady feeding, significant mergers, and episodic bursts of activity, leading to the behemoth anchoring the galaxy's heart. The evidence underscores the interconnected evolution of black holes and galaxies, a cosmic dance stretching back nearly to the universe's origin. Each new observation adds detail to this grand narrative, illustrating a black hole that has grown, evolved, and continues to shape its galaxy. Black holes are among the universe's most mysterious objects. They are regions in space where gravity is so intense that nothing, not even light, can escape. To understand how they form, what they look like, and their importance, it's helpful to start with the basics. Imagine a star much more massive than our Sun. When such a star exhausts its nuclear fuel, it can no longer resist gravity's inward pull. The core collapses, and if the remaining mass exceeds about 3 times the Sun's mass, it compresses beyond neutron degeneracy pressure's ability to hold it up. The result is a black hole, a point in space with a gravitational pull so strong that space-time caves inward. This is called a stellar black hole, usually formed from the remnants of massive stars ending their life cycles in supernova explosions. Stellar black holes tend to have masses several times that of the Sun, typically between 5 and 20 solar masses. They are scattered throughout our galaxy, often in binary systems with a normal star. If the star gets close enough, the black hole can pull material from it, creating an accretion disk, a glowing, swirling ring of hot gas spiraling into the black hole. This process heats the material to high temperatures, causing it to emit X-rays detectable from Earth or space telescopes, providing indirect evidence of their presence. At galaxy centers, including our Milky Way, a different type of black hole predominates: supermassive black holes. These giants are vastly larger, containing millions to billions of times the Sun's mass. They aren't formed from a single star's collapse, but grow over billions of years by accreting gas, dust, and even smaller black holes that come too close. The key difference between stellar and supermassive black holes is their size, mass, and formation. Stellar black holes are the final products of massive star evolution. When such stars run out of fuel and explode, the core collapses into a black hole about the size of a few cities on Earth. Their formation process, stellar evolution and gravitational collapse, is well understood. Supermassive black holes grow through accretion and mergers. Their origins remain an area of active research. Some theories suggest they began as seed black holes formed early in the universe, perhaps from the direct collapse of massive gas clouds or the remnants of the first stars. Over billions of years, these seeds accumulated more mass, eventually evolving into the supermassive black holes seen today. Supermassive black holes significantly influence galaxy formation and evolution. They act as cosmic anchors, shaping the structure and dynamics of their host galaxies. Their growth can trigger star formation by funneling gas to the galactic center, or suppress it through energetic outflows called jets, or winds that blow gas away. This interaction, called coevolution, indicates that galaxy and black hole formation are deeply linked. Studying these black holes requires different methods. Stellar black holes are relatively close and emit X-rays during accretion, detectable with X-ray observatories. They sometimes appear as X-ray binaries, where the black hole's gravity pulls material from a star, forming a luminous accretion disk that shines in high-energy wavelengths. Supermassive black holes pose greater observational challenges because they are often obscured by gas and dust, and are located at galaxy centers, sometimes far away. Direct imaging of their event horizons, beyond which nothing can escape, is now possible using advanced telescopes. For instance, the Event Horizon Telescope captured the first image of a black hole shadow in galaxy M87, providing direct visual evidence of their existence. In our galaxy, astronomers observe stars orbiting at high speeds around Sagittarius A, revealing the black hole's immense gravity, estimated at about 4 million solar masses. Understanding the differences between stellar and supermassive black holes sheds light on cosmic history. The earliest universe likely saw the formation of seed black holes, probably from the collapse of massive gas clouds or the remnants of the first stars, that then grew through accretion and mergers, evolving into supermassive black holes. Their presence helps explain rapid galaxy growth and the complex relationship between galaxies and their centers. Despite the size difference, all black holes share core qualities. They are defined by an event horizon, a boundary beyond which nothing escapes, and by a singularity, a point where density becomes infinite and our current physical theories break down. While we cannot look directly into a black hole, indirect evidence such as stellar motions, accretion disk properties, and gravitational waves from black hole mergers helps physicists understand their nature. Black holes are also valuable laboratories for testing fundamental physics, especially Einstein's general relativity and quantum mechanics. They challenge our understanding of gravity, space, and time. Supermassive black holes, with their enormous influence, are central to probing these foundational questions, connecting cosmic scales with quantum phenomena. In contemplating these cosmic titans, we see that black holes are not merely vacuum cleaners or destructive entities. They are essential drivers of cosmic evolution and keys to understanding the universe's deepest mysteries. Whether tiny stellar remnants or colossal supermassive giants, black holes continue to push scientific discovery, revealing some of the universe's most enigmatic and awe-inspiring features. At the boundary of a black hole lies the event horizon, a term evoking mystery and profundity. It's not a physical surface like a planet's edge or a fruit's skin, but a mathematical concept, a point of no return. Imagine standing at the edge of a dark abyss. Beyond this boundary, the gravity is so intense that nothing, not even light, can escape. This is the essence of the event horizon, the ultimate boundary beyond which escape is impossible. Black holes are regions where matter compresses into tiny volumes, creating gravity so strong that space-time itself curves dramatically. At the core, or singularity, gravity is thought to become infinite, though this remains theoretical and challenges current physics. Surrounding the singularity is the event horizon, serving as its defining border. Anything crossing it spirals inward, disappearing into the black hole, never influencing the outside universe again. Why is the event horizon critical? Its importance lies in both the physics it embodies and the observational challenges it presents. From a physics viewpoint, it marks where classical physics, particularly Einstein's general relativity, predicts extreme phenomena. Space-time becomes warped to such a degree that traditional notions of space and time break down. Studying the event horizon offers insights into these conditions, testing gravity theories and the nature of space-time. The event horizon acts like a one-way membrane. From outside, an object falling in appears to slow down and freeze at the horizon due to gravitational time dilation. To the infalling object, crossing the horizon is uneventful, and it continues inward. This differing experience raises questions about the nature of information, entropy, and space-time, ongoing puzzles in physics. Understanding the event horizon is also key to the black hole information paradox. Quantum mechanics suggest information about a system's initial state cannot be destroyed, yet matter and radiation crossing the horizon appear to be lost forever. The paradox questions whether information is erased or preserved, and resolving it could unify quantum mechanics and gravity, leading to revolutionary insights. Observationally, the event horizon remains elusive. It's effectively a dark point of no return, hidden in darkness. Instead, scientists study the environment around black holes, like the hot luminous accretion disk just outside the horizon, and analyze emitted radiation. In 2019, the Event Horizon Telescope, a global network of radio dishes acting as a single planet-sized telescope, produced the first direct image of a black hole's shadow in galaxy M87. This silhouette against the glowing disk provided visual evidence of the event horizon, confirming Einstein's predictions about its size and shape. This achievement is groundbreaking, opening a new era in black hole studies. It confirms theoretical models and enables more detailed investigations, revealing how matter behaves near the boundary, how strong gravity influences radiation from the accretion disk, and what the shadow reveals about spacetime geometry around black holes. The event horizon also has significant implications for cosmology and galaxy evolution. Supermassive black holes like Sagittarius A in our Milky Way grow by merging and consuming matter. The size of their horizons offers clues about their history and the process of galaxy formation. By studying these horizons, astronomers trace the timeline of galactic growth and the feedback processes influencing star formation and cosmic structure. Another key aspect linked to the event horizon is Hawking radiation, a theoretical prediction by physicist Stephen Hawking in the 1970s. Near the horizon, quantum effects would cause black holes to emit a faint glow of radiation, leading to gradual mass loss and eventual evaporation. While this radiation has yet to be observed directly, it underscores the significance of the event horizon as a boundary where quantum phenomena intertwine with gravity. the event horizon also underscores the limits of current physics. Near this boundary, classical understanding gives way to mysteries rooted in quantum physics. Efforts are underway to develop a quantum theory of gravity capable of describing what occurs at or beyond the horizon. Whether the horizon is a sharp boundary, a fuzzy quantum region, or something more exotic remains an open question. Recent theories, such as the firewall hypothesis, suggest that the horizon may not be smooth as Einstein predicted, but could contain highly energetic zones, firewalls that destroy anything falling in. Others propose that the horizon might be an illusion, with the true boundary located elsewhere, or that new physics could eliminate the singularity entirely. These ideas spring from the fundamental importance of the event horizon. It's not just darkness, but a doorway to profound cosmic mysteries. In essence, the event horizon makes black holes more than dense matter collections. It is the ultimate frontier for understanding gravity, quantum physics, and space-time. It's where our current laws break down, and new physics must emerge. Studying it pushes human knowledge forward and could unlock answers to some of the universe's most enigmatic questions. As observations continue and models improve, the event horizon remains a captivating symbol of cosmic mystery. It's a boundary that reveals the limits and potentials of physics, challenging us to explore beyond known theories. Future research aims to uncover what truly happens at or near the horizon, whether it's a sharp boundary, a quantum fuzziness, or something entirely different. Each discovery helps piece together the puzzle of how our universe works at its most fundamental level. In summary, the event horizon is essential for understanding black holes, acting as both a physical boundary that challenges our theories and a window into the workings of gravity, quantum mechanics, and space-time. Its study offers insights into cosmic evolution, the fabric of the universe, and the fundamental laws that govern reality. It remains one of the most profound and intriguing concepts in astrophysics, continually inspiring new research and ideas. To understand black holes like Sagittarius A at our galaxy's centre, we must explore the physics principles that describe these phenomena, chiefly Einstein's general relativity and related theories. Before Einstein's insights, black holes were thought purely theoretical, solutions to Einstein's equations considered too exotic to exist naturally. Today, black holes are recognized as real, gravitationally collapsed objects, with Sagittarius A exemplifying a supermassive black hole containing millions of times the Sun's mass. Einstein's general relativity redefines gravity, contrasting with Isaac Newton's view of gravity as a force between masses. Instead, Einstein proposed that gravity results from the curvature of space-time itself, a four-dimensional fabric warped by mass and energy. Think of space-time as a vast woven fabric, with massive objects creating profound dips or warps. These warps aren't forces, but changes in space and time's geometry, influencing how matter moves and light travels. When immense mass is compressed into a tiny volume, as in a collapsing star, the space-time curvature becomes extreme. The boundary where gravity is so intense that nothing, not even light, can escape, is called the event horizon, marking the black hole's edge. Inside this horizon, warping increases infinitely at the singularity. Where classical physics breaks down, densities become infinite, and current theories cannot fully describe the environment. Sagittarius A is thought to harbour a supermassive black hole with significant rotation, adding complexity to the surrounding space-time, described by solutions like the Kerr metric. Escape velocity, the speed required to leave a gravitational field, is key. When matter collapses within a certain radius, escape velocity exceeds light speed, trapping everything inside. At the core, matter contracts into a singularity, an infinitely dense point, around which space and time are fundamentally altered. Inside the event horizon, the radial coordinate becomes time-like. Falling inward becomes as inevitable as moving forward in time outside the black hole. No escape exists, and objects inevitably reach the singularity. Quantum mechanics adds complexity to this picture. Unlike classical physics, which predicts black holes as ultimate traps, quantum principles governing tiny particles introduce new effects. Stephen Hawking's work in the 1970s showed black holes emit faint radiation, Hawking radiation, caused by quantum effects near the event horizon. Quantum fluctuations create pairs of particles. Sometimes, one falls into the black hole, the other escapes, causing the black hole to slowly lose mass over time. This evaporation challenges the classical idea that nothing can escape, raising questions about information conservation. The interplay of gravity and quantum mechanics exposes fundamental conflicts. Einstein's geometric description excels on large scales, stars, galaxies, but breaks down at the singularity, where quantum effects dominate. Conversely, quantum theory describes particles but doesn't incorporate gravity. Developing a quantum gravity theory, such as string theory or loop quantum gravity, is a major goal in physics, aiming to reconcile these frameworks and resolve puzzles like the nature of singularities and the black hole information paradox. In astrophysics, Einstein's general relativity is crucial for analysing observations near Sagittarius A. Precise measurements of stars orbiting close to the galactic centre reveal enormous mass concentrated within a tiny volume, about 4 million solar masses within a region smaller than our solar system. These measurements, obtained via advanced telescopes and interferometry, confirm the presence of a supermassive black hole, as no other object fits these parameters. Einstein's equations allow modelling the gravitational potential, predicting stellar motions, thus testing the theory's validity in intense gravitational environments. General relativity also predicts gravitational lensing, the bending of light by gravity, a phenomenon observed across the universe. Near black holes, light from background stars or accretion disks bends dramatically, creating multiple images, Einstein rings, or the black hole's shadow. The Event Horizon Telescope's recent imaging of Sagittarius A captured this shadow, a dark region caused by light bending at the photon sphere, where photons can orbit. This image matches Einstein's spacetime curvature predictions and marks a milestone in black hole imaging. Time dilation, another key consequence, occurs in strong gravity. Near an event horizon, spacetime curvature causes clocks to run more slowly relative to distant observers. From afar, falling objects seem to freeze at the horizon, never crossing it. But the infalling object passes through smoothly. This observer-dependent paradox makes black holes ideal laboratories for studying space, time, and causality's fundamental nature. Black holes also influence galactic centers, affecting galaxy evolution through accretion and jets. Sagittarius A emits faint jets and radiation powered by material falling into its accretion disk, converting gravitational energy into electromagnetic emissions. These observable processes are explained using Einstein's equations, which describe the interaction between matter, radiation, and spacetime curvature. The dynamics shape the evolution of their host galaxies and influence cosmic evolution. Research continues into black hole structure and event horizon physics, exploring classical and quantum interfaces. Because black holes create extreme conditions, they act as natural laboratories for understanding fundamental laws. They raise profound questions. What occurs at the singularity? Is information preserved? Can quantum effects prevent singularities? These questions challenge and expand modern science, pushing the boundaries of conceptual understanding. Ultimately, black holes like Sagittarius A demonstrate how Einstein's general relativity provides a precise framework for understanding the warping of spacetime and gravity in the universe's most extreme environments. They test our theories and point toward new physics beyond existing models. Astronomical observations, from stellar orbits to shadow imaging, confirm Einstein's predictions and uncover cosmic mysteries. These invisible giants reveal the fabric of reality, guiding us toward a deeper understanding of the universe's fundamental laws. From spacetime warping to quantum effects suggesting new physics, black holes symbolize the bridge between what is known and what remains to be understood. A testament to the profound power of physical laws shaping the cosmos, peering directly into the very edge of a black hole's event horizon presents formidable scientific challenges. The event horizon, known as the point of no return, is a boundary beyond which nothing, not even light, can escape Sagittarius A's intense gravity. Despite its significance, capturing images or data from this boundary remains a major hurdle due to extreme conditions and limitations imposed by physics, technology, and the vast cosmic scale. The primary obstacle is the vast distance, approximately 26,000 light-years from Earth. Any message or image from Sagittarius A would take 26,000 years at light speed to reach us. To observe phenomena at the event horizon, astronomers detect tiny photons and signals emitted as matter spirals inward, precisely where gravity warps spacetime so drastically. However, capturing these signals is akin to observing a flickering candle across a storm-tossed ocean, as the signals are faint and often obscured by cosmic dust, gas, and the galaxy's electromagnetic noise. The surroundings emit across the entire electromagnetic spectrum, radio, infrared, X-ray, requiring different techniques, instruments, and conditions. These signals are drowned out by background noise, demanding highly sensitive equipment to distinguish the black hole's faint signals from cosmic interference. Another challenge lies in the unpredictable and turbulent nature of the signals. Matter falling into Sagittarius A heats intensely as it accelerates and compresses near the event horizon, emitting variable, sometimes intense radiation. These emissions often fluctuate over minutes, hours, or days, making consistent imaging difficult. Unlike steady stars, the environment around a black hole is chaotic, with swirling matter, relativistic jets, and twisting magnetic fields. This turbulence produces flickering emissions, complicating efforts to produce clear, high-resolution images. A significant breakthrough is Very Long Baseline Interferometry, VLBI, which links radio telescopes globally to form a giant Earth-sized dish with incredible resolution. Yet, imaging Sagittarius A's event horizon with VLBI is still complex. It requires perfect synchronization of telescopes thousands of miles apart, ultra-stable atomic clocks, and high-speed data transport for processing. The wavelengths used, like millimeter waves, are affected by Earth's atmosphere, especially water vapor, which can distort signals. Careful calibration and corrections are necessary to mitigate atmospheric effects and obtain clear data. Furthermore, Sagittarius A's environment changes rapidly. Variability in accretion rates, how much matter falls into the black hole, can happen over minutes or hours, affecting brightness and structure. This makes stitching together images taken over days or weeks challenging, as reflections of short-term fluctuations must be accounted for. Achieving an accurate snapshot of the event horizon's shape involves patience, precision, and multiple iterations. Theoretical limitations also play a role. Near the event horizon, physics is governed by Einstein's general relativity, but under extreme conditions, quantum effects might be important, a domain still not fully understood. Current models of matter behavior in strong gravitational fields are complex but incomplete. This complicates interpretation of observational data, as scientists rely on simulations that depend on assumptions which might be challenged or refined as new data emerges. Technological advances are essential to push boundaries. Developing detectors sensitive enough to discern faint signals in noisy environments and processing immense data volumes, sometimes petabytes, are ongoing challenges. Improving computational techniques, data analysis algorithms, and hardware infrastructure is crucial to convert raw observations into clear images of the event horizon. Despite these hurdles, progress is impressive. In 2019, the Event Horizon Telescope, EHT, collaboration released the first ever image of a black hole in galaxy M87. This achievement showed that perseverance, innovation, and global coordination can reveal black hole shadows, providing direct visual evidence of their event horizons. The image displayed a bright ring of light framing a dark shadow, the black hole's silhouette, demonstrating the ability to visualize these cosmic giants directly. Applying similar techniques to Sagittarius A introduces additional complexities. Its event horizon appears roughly 20 times smaller in the sky than M87's, demanding even finer resolution. The environment's rapid variability on short timescales further complicates imaging, as the surroundings are constantly changing during observations. In essence, observing Sagittarius A's event horizon is like trying to photograph a tiny, fiery whirlpool in a stormy, distant ocean, constantly flickering and shifting amidst cosmic noise and atmospheric distortions. It pushes technological frontiers, refines models of extreme physics, and requires a global network of observatories working in unison. Overcoming each challenge brings us closer to understanding black holes and the fundamental laws governing the universe. Every incremental step transforms the inscrutable into the observable, bringing the mysterious boundary of the event horizon into scientific reach. To uncover the mysterious nature of Sagittarius A, scientists turn to a powerful tool, models. Since direct observation of the black hole itself is impossible, no light escapes its grasp. researchers rely on sophisticated computer simulations and theoretical frameworks to interpret the data collected by telescopes. Think of models as virtual laboratories where the laws of physics are put into action, allowing scientists to compare what they expect to observe with what they actually see. The process begins with gathering observational data, measurements of star movements, emissions across diverse wavelengths, and signals from the accretion material spiraling into the black hole. These observations serve as the backbone for the modelling efforts. For example, astronomers track the orbits of stars that skitter close to Sagittarius A. These stellar motions are like celestial choreography, subtly influenced by the black hole's immense gravity. By analysing their paths over many years, scientists can calculate the mass of the black hole with remarkable precision. Once the mass is known, the models come into play to understand the environment around it. For instance, the accretion process, where gas and dust swirl into the black hole, emits intense radiation, especially in the X-ray and radio wavelengths. Models of accretion disks, flattened, luminous structures of inflowing material, simulate how matter behaves under extreme gravity and magnetic fields. These simulations incorporate Einstein's general relativity, which predicts how space-time warps around such dense objects. A crucial aspect of modelling Sagittarius A involves the Event Horizon Telescope, an array of radio telescopes scattered around the globe working in unison. Using very long baseline interferometry, they create images with incredible resolution, enough to glimpse the shadow of the black hole's event horizon. To interpret these images, scientists develop general relativistic magnetohydrodynamic models, which combine the physics of magnetic fields, plasma dynamics, and relativistic gravity. These models generate synthetic images that can be compared directly with observations. If the simulated shadow and surrounding emission match the actual images, scientists gain confidence in their understanding of the black hole's properties. Furthermore, models help probe the spin of the black hole, how fast it's rotating. Spin influences the shape of the shadow and the behavior of nearby matter. By running simulations with different spin parameters, researchers see how the model's predictions change. When the simulated and real data align, they can estimate how rapidly Sagittarius A is spinning. This spin measurement is vital because it informs theories about the black hole's growth history and the dynamics of the galactic center. Models aren't limited to the immediate vicinity of the black hole. They also extend to larger scales within the galaxy. Researchers simulate how the black hole influences star formation, gas flows, and even the growth of the galaxy itself. These larger-scale models integrate data from multiple observations, including the distribution of gas and stars, to understand the black hole's role in shaping its environment over cosmic time. Another fascinating aspect involves testing Einstein's theory of general relativity. Since conditions near Sagittarius A are extreme, they provide a natural laboratory for gravity's most intense regime. Scientists develop models that incorporate predictions of how space-time should behave in strong gravitational fields. By comparing these predictions with the precise motions of stars and the structure of emitted radiation, they can verify or challenge our current understanding of fundamental physics. Building these models is a complex, iterative process. Scientists start with initial assumptions, run simulations, compare the results with observational data, and refine their models accordingly. This cycle continues until the models accurately reproduce the observed phenomena. This approach enables researchers to extract information that cannot be directly measured, such as the black hole's spin, the configuration of magnetic fields, or the properties of the accretion flow. Ultimately, models serve as a bridge between the observed universe and the hidden depths of black holes. They allow scientists to make educated inferences about properties that are otherwise inaccessible, turning faint signals into detailed portraits of these cosmic giants. Through continual improvements in models and the influx of higher quality data, our picture of Sagittarius A grows clearer, bringing us closer to understanding the fundamental forces that govern our galaxy, and, by extension, the universe itself. To peel back the layers of the universe's most mysterious giants like Sagittarius A, astronomers rely on a fascinating array of instruments and innovative methods, turning the invisible into something we can study and understand. Given that Sagittarius A is shrouded in darkness, absorbing all light that ventures too close, scientists harness the power of indirect observation, reading faint radiation and motion that reveal its presence and nature. One of the primary tools in astronomers' arsenal is radio telescopes. Unlike optical telescopes that capture visible light, radio telescopes detect electromagnetic waves with much longer wavelengths. Sagittarius A emits a faint but persistent signal in radio frequencies from hot gases swirling in its strong gravitational grip and charged particles spiraling in magnetic fields. By tuning into these emissions, scientists gather vital data about the black hole's environment. The design of radio telescopes has evolved for remarkable sensitivity. Large single-dish antennas, some spanning over 100 meters, serve as our ears tuned to the cosmos. These massive dishes collect radio waves and focus them onto sensitive receivers. Even more groundbreaking is the technique called Very Long Baseline Interferometry, VLBI. This approach synchronizes multiple radio telescopes scattered across the globe, creating a virtual Earth-sized telescope. This virtual dish peers with extraordinary resolution, allowing astronomers to image Sagittarius A with unprecedented detail, capturing features such as the accretion flow, the swirling matter spiraling inward, and phenomena like plasma jets and the event horizon's shadow. While the radio window is vital, it's only part of the picture. Telescopes operating at other wavelengths extend our reach into different facets of Sagittarius A's environment. Infrared observatories, such as the Very Large Telescope in Chile, utilize infrared light to peer through dense clouds of gas and dust, obscuring the galactic center. Adaptive optics systems improve image clarity, enabling astronomers to track individual stars near Sagittarius A. Monitoring their accelerated orbits reveals the black hole's gravitational influence, confirming its mass and dominance. Optical telescopes, although less effective directly at observing Sagittarius A due to dust, contribute indirectly by studying stellar motions in the galactic core. Observatories like Keck have captured the orbits of stars such as S2. Tracking these trajectories over years or decades allows scientists to infer the black hole's properties with remarkable precision. X-ray observatories add another crucial layer. Sagittarius A occasionally exhibits flares, short bursts of high-energy radiation detected by satellite instruments like NASA's Chandra or ESA's XMM Newton. These flares originate from energetic processes near the event horizon, where matter heats to millions of degrees as it spirals inward. Analyzing their timing and spectral properties offers insights into the mechanisms fueling accretion and jet formation. Terrestrial telescopes also play a role, particularly in the infrared and sub-millimeter ranges. The Atacama Large Millimeter Submillimeter Array, ALMA, in Chile, provides exquisite sensitivity to faint signals emitted by molecules near Sagittarius A. This helps scientists trace the flow of material feeding the black hole, shedding light on how black holes grow over cosmic time. Interpreting this data requires sophisticated methods such as interferometry, spectroscopy, and imaging reconstruction. Interferometry combines signals from multiple telescopes for higher resolution. Spectroscopy decomposes radiation into component wavelengths, revealing velocities, temperatures, and compositions of infalling matter. Image reconstruction algorithms process sparse and noisy data, producing detailed images of regions close to the event horizon. Among the most notable techniques is the Event Horizon Telescope, EHT. This global collaboration synchronizes radio telescopes worldwide to form a giant Earth-sized virtual telescope. Observing at millimeter wavelengths, the EHT aims to image the black hole's shadow, the dark area against the glowing accretion flow predicted by Einstein's theory of general relativity. Over recent years, the EHT successfully produced the first image of a black hole's shadow in galaxy M87, and similar efforts target Sagittarius A. Complementing these observational methods are computational simulations. Using supercomputers, researchers develop models of matter behavior under intense gravity, magnetic fields, and high-energy conditions. Comparing these models with observational data advances our understanding of accretion disks, relativistic jets, and the physics near the event horizon. Another technique involves gravitational lensing, where the black hole's gravity bends light from background sources. Analyzing these distortions helps refine measurements of the black hole's mass and spin, revealing its influence on surrounding spacetime. The study of Sagittarius A exemplifies the synergy of multi-wavelength astronomy, international collaboration, and advanced technology. Every instrument, radio, infrared, optical, X-ray, and sub-millimeter, serves as a different lens into its complex environment. Combining these observations, along with data processing and theoretical modelling, allows scientists to unveil the secrets of our galaxy's core, transforming the once invisible titan into a subject of scientific inquiry. Advances in technology promise to deepen our understanding further. Upgraded telescopes, new interferometric techniques, and refined computational models will allow us to probe even closer to the event horizon. The shadow of Sagittarius A will become less a shadow and more a window into the laws of physics. The quest to understand these cosmic giants showcases human ingenuity and relentless curiosity about the universe we inhabit. Radio telescopes are crucial tools in studying the galactic center, especially Sagittarius A. Unlike optical telescopes, which rely on visible light, radio telescopes detect radio waves emitted by cosmic phenomena. This is vital because the galaxy's center is obscured by dense clouds of dust and gas that absorb and scatter visible light, making optical observations nearly impossible. Radio waves, however, can penetrate these clouds, providing a clear view into the Milky Way's core. One major contribution of radio telescopes is capturing electromagnetic radiation from materials swirling around Sagittarius A. Although the black hole itself doesn't emit light, the accretion disk of gas, dust and debris spiraling into it heats up to extreme temperatures, emitting strongly in radio frequencies. By observing these emissions, astronomers can study the behavior of matter near the black hole, gaining insight into the dynamics of accretion, which is otherwise invisible. Radio telescopes are also instrumental in mapping the orbits of stars and gas clouds near Sagittarius A. Precise measurements of their motions reveal stars orbiting at extraordinary speeds around an unseen mass, leading to the conclusion that a supermassive black hole, about 4 million times the Sun's mass, resides there. These stellar orbits act as test particles, helping scientists infer black hole properties such as mass and size without direct observation. Advances like very long baseline interferometry, VLBI, vastly improve resolution by linking multiple antennas across great distances, effectively creating a telescope the size of Earth. This technique allows astronomers to image regions near Sagittarius A with remarkable detail. Such high-resolution imaging has revealed structures like the black hole's shadow, an apparent silhouette against the glowing and falling material, offering critical insights into the black hole's environment. Radio observations also shed light on the variability and activity of Sagittarius A. The black hole produces flares, sudden brightness increases lasting from minutes to hours. Monitoring these flares helps researchers understand the physics of accretion and energy release near the event horizon. Tracking their timing and spectral changes provides clues about magnetic fields, plasma turbulence, and particle acceleration operating close to the black hole. Polarized radio emission from the galactic center is another key area of study. The polarization indicates the presence and structure of magnetic fields in the accretion disk and nearby regions. Magnetic fields are believed to influence jet and outflow formation, which carry away angular momentum and regulate matter inflow. Analyzing polarized signals helps astronomers understand how magnetic forces shape black hole activity. Radio telescopes also detect energetic particles accelerated at the galactic center. Cosmic ray electrons emit synchrotron radiation, radio waves from spiraling along magnetic fields, forming diffuse structures like radio lobes and filaments. These features serve as fossil records of past energetic episodes, revealing the black hole's activity history over thousands or millions of years. Beyond imaging, radio telescopes facilitate the detection of transient phenomena like fast radio bursts, FRBs, intense, short pulses of radio waves often lasting milliseconds. Although their origins remain unclear, their detection and localization open new research avenues. Understanding whether these bursts relate to Sagittarius A or other energetic processes deepens our grasp of the black hole environment and large-scale cosmic phenomena. Radio observations also improve knowledge of the interstellar medium, the gas and dust surrounding the galactic center. By examining spectral lines and emission features of atoms and molecules, scientists assess composition, density, and temperature of the clouds feeding the black hole. This information helps elucidate black hole fueling, star formation, and the galaxy's evolution. Large observatories like the Atacama Large Millimeter Sub-Millimeter Array, ALMA, have been instrumental. These arrays combine many antennas over long baselines, functioning as a single colossal instrument capable of detecting faint signals from the galaxy's core. They enable detailed spectral analysis, revealing chemical processes and physical conditions close to the black hole. Future and ongoing radio projects promise to revolutionize our understanding even further. Projects like VLBI aim to produce real-time, dynamic images of the event horizon, potentially creating movies showing the swirling accretion flow and the black hole's shadow, offering an unprecedented visualization of a black hole's environment. Historically, radio telescopes were among the first tools to hint at the black hole's existence. The discovery of synchrotron radiation from the galactic center in the late 20th century evidenced energetic phenomena tied to the region. Over decades of observations, a growing body of evidence has uncovered the intricate interactions of matter and energy governed by the black hole's gravity. Without radio telescopes, much of what is known about Sagittarius A would remain speculative, veiled behind cosmic dust and gas. They serve as our eyes and microscopes into the Milky Way's hidden core, piercing dust, tracing stellar motions, mapping magnetic fields, detecting energetic particles, and capturing transient flares with high precision. Their capabilities enable us to explore the invisible giant at the galaxy's center as if looking through a window, revealing a turbulent, energetic, and enigmatic environment. By providing detailed images, tracking dynamic activity, and studying the physical conditions near Sagittarius A, radio telescopes have transformed our understanding of black holes. They continue to push the frontiers of knowledge, promising even more profound insights into these cosmic giants, their influence on galaxy evolution, and the fundamental physics of extreme gravity and magnetism that govern the universe. The Event Horizon Telescope, often called the EHT, is a marvel of modern astrophysics and a groundbreaking tool for unveiling black holes' mysteries. To understand its role, it's essential to grasp the challenge it was designed to overcome. Black holes are invisible in the traditional sense. They do not emit light and trap everything, including electromagnetic radiation, beyond their event horizon. So, how can scientists image something that cannot be directly observed? The answer involves extraordinary technology, innovative techniques, and some cosmic detective work. The EHT operates as a global network of radio telescopes synchronized as a single, Earth-sized virtual observatory. Imagine multiple telescopes across continents, from Hawaii and Arizona to Spain, South Africa, and the South Pole, integrating signals through a process called Very Long Baseline Interferometry, VLBI. This technique allows the combined array to achieve an angular resolution vastly better than any single telescope, effectively turning the entire planet into a giant, super-sharp radio receiver. This incredible resolution enables astronomers to resolve features as small as the event horizon of black holes millions or billions of light-years away. Scientists focused the EHT on the supermassive black hole at the center of galaxy M87, marking a historic journey into uncharted territory. This black hole, called M87C, is among the most massive, containing billions of times the Sun's mass. Its size and relative proximity made it an ideal initial target. The challenge was immense. The apparent size of the event horizon from Earth is comparable to the grapefruit on the Moon viewed with a special camera. Overcoming this required not just high resolution, but also precise calibration and sophisticated data processing. The process begins with telescopes collecting radio waves emitted by hot, ionized gas swirling around M87LAN at speeds approaching light. This accretion disk heats up and becomes luminous in radio frequencies, especially millimeter wavelengths. These emissions, while indirect, carry vital information. As the gas orbits and accelerates, it interacts with the black hole's strong gravitational field, producing gravitational lensing effects and a distinctive shadow, the dark region where light cannot escape due to the event horizon. Because signals from all telescopes arrive at different times, due to their physical separation, the EHT uses VLBI. They record time-stamped signals at each location, with atomic clocks of extraordinary precision so they can be matched and correlated later. This process synthesizes a detailed interference pattern, which is then analyzed with complex algorithms. Due to the enormous data volume, these recordings are shipped to supercomputers for correlation, calibration, and imaging. Throughout this process, dealing with faint signals and atmospheric disturbances is crucial. Advanced algorithms like clean and regularized maximum likelihood methods help reconstruct images from the interferometric data. It's like assembling a high-definition puzzle from millions of tiny radio wave data pieces, each representing a small slice of the sky's radio emission. The culmination of these efforts was the first direct image of a black hole's shadow, a bright ring of light surrounding a dark circular region where the event horizon lies. This shadow is more than a striking image. It's a direct test of Einstein's general relativity under extreme conditions. Its size and shape match predictions for a black hole of known mass, providing strong evidence supporting current understanding of black holes. Beyond the visual impact, the EHT yields scientific insights. By analysing the shadow's shape and size, scientists can measure the black hole's mass and spin. Variations in the ring's brightness and structure over time reveal turbulence and dynamic processes near the event horizon. The EHT also tests the limits of physics. Are these shadows perfectly round, as Einstein predicts, or do they show deviations that could indicate new physics? Success with M87 opened the door to imaging Sagittarius A, our galaxy's central black hole. While Sagittarius A arm is less massive than M87, it's much closer, making it an ideal target for future high-resolution imaging. However, its environment is more dynamic and complex, posing additional challenges. Efforts to peer closer to Sagittarius A are underway, with promising insights into our galactic neighbourhood's black holes. The EHT's role extends beyond creating iconic images. It fundamentally changes our understanding of black holes and their environments. It confirms the existence of event horizons, mysterious boundaries beyond which nothing can escape. It tests Einstein's general relativity in the universe's strongest gravitational fields. It also sheds light on black hole growth and evolution, crucial for understanding galaxy formation, since supermassive black holes seem central to galactic development. In essence, the EHT exemplifies human ingenuity and international cooperation. It combines advanced technology, astrophysics, and computing to turn the invisible into a visual form. It demonstrates that even the universe's most elusive objects, hidden behind their event horizons, can be glimpsed indirectly. This pushes astronomy's boundaries, revealing new facets about the universe and our place within it. Each black hole image deepens our understanding of reality, space-time, and the cosmos. The success with M8710 proved that imaging black hole shadows is possible, paving the way for further discoveries. By expanding to other black holes, especially Sagittarius A's, scientists hope to refine measurements, test theories, and explore fundamental physics. The EHT's ongoing advances promise deeper insights into the nature of gravity, quantum effects near singularities, and the universe's fundamental laws. It exemplifies how collaboration, innovation, and persistence can unlock the universe's deepest secrets, transforming cosmic mysteries into tangible knowledge. Infrared and X-ray observations are essential for understanding Sagittarius A and its environment, complementing radio data. While radio waves provided the first images of the black hole's shadow, infrared and X-ray wavelengths reveal different, interconnected aspects of this cosmic object. Radio observations have been crucial in tracking stars orbiting close to Sagittarius A, revealing its immense gravitational pull. These measurements allow precise determination of the black hole's mass and size. The radio waves emitted by accretion flows, hot plasma spiraling inward, offer insights into the structure and dynamics of the surrounding matter. However, radio data alone can't capture all phenomena, especially the energetic processes near the event horizon. Infrared observations penetrate dust clouds that often obscure the galaxy's core, offering a window into Sagittarius A's immediate environment. Infrared telescopes have detected flares, sudden bursts of emission, originating from regions just outside the event horizon. These flares likely result from magnetic reconnection, or hotspots orbiting very close to the black hole. Monitoring infrared flares helps astronomers understand the turbulent behavior of matter in extreme gravitational and magnetic fields, shedding light on how matter heats and accelerates near the black hole. Processes difficult to observe through radio emissions alone. Furthermore, infrared data enable high-precision tracking of individual stars and gas clouds. Because infrared light isn't heavily absorbed by interstellar dust, it reveals the orbital paths of stars like S2, which come very close to Sagittarius A. Tracking these orbits over years has been vital in confirming the black hole's mass and the stability of its gravitational influence. This dynamic information complements radio measurements, providing detailed kinematic data about how the gravitational field affects the immediate surroundings. X-ray observations probe the most energetic phenomena associated with Sagittarius A, revealing the aftermath of matter spiraling inward and reaching near-light speeds. As matter accelerates, it heats up to millions of degrees, emitting X-ray radiation. X-ray telescopes have detected sporadic flares from Sagittarius A, indicating that accretion is highly variable and turbulent. These high-energy bursts provide insights into physical processes occurring very close to the event horizon, where magnetic fields interact strongly with infalling plasma. X-ray data also reveal the presence of hot plasma near the black hole, heated by shocks, magnetic reconnection, and viscous dissipation. This creates energetic environments that influence accretion flows. By studying the timing and spectral properties of X-ray flares, scientists can infer conditions near the event horizon, such as density, temperature, and magnetic field strength. When combined, infrared and X-ray observations deepen our understanding of Sagittarius A by providing a layered view of its environment. Infrared observations highlight star motions and matter behavior outside the event horizon. They capture phenomena like hotspots and magnetic activity, shedding light on the physics of accretion disks and the boundary between stellar material and the black hole's event horizon. X-ray observations focus on the most energetic events and plasma heating near the event horizon. The variability, spectral signatures, and timing of X-ray emissions reveal turbulent mechanisms fueling the black hole's growth. Together, these wavelengths reveal different facets of black hole activity. Infrared probes the dynamics of matter just outside, while X-rays explain high-energy events occurring closer in. Radio data, infrared, and X-ray observations form a comprehensive toolkit. Radio telescopes map the broad structure of accretion flows and star orbits, illustrating Sagittarius A's gravitational influence. Infrared observations delve deeper into the near-horizon environment, capturing transient phenomena like flares that illuminate magnetic and relativistic processes. X-ray observations, in turn, focus on the most energetic, violent events occurring close to the black hole, exposing conditions in its immediate vicinity. These three wavelengths are like different lenses observing the same object, from the wider gravitational dance of stars in the galaxy's core to the intense turbulence near the black hole itself. Each adds a piece to the puzzle, enabling astronomers to build a more complete picture of how supermassive black holes grow and influence their galaxies. It's through coordinated multi-wavelength observations that astronomers are unraveling Sagittarius A's deepest mysteries. No single wavelength offers the full story. Together, these data form a symphony that enhances our understanding of one of the universe's most enigmatic and powerful objects. Future technological advances and collaborations will expand this multifaceted approach, pushing the boundaries of our knowledge about black holes, galaxy evolution, and fundamental physics governing the cosmos. Word count 757. Recent advancements in technology have greatly expanded our ability to study the Milky Way's core, especially Sagittarius A's, transforming our understanding of this supermassive black hole. Key innovations include enhanced radio interferometry, space-based observatories, advanced data processing, and new detectors, each peeling back layers of cosmic mystery. One major breakthrough is improvements in very long baseline interferometry, VLBI. Traditional radio telescopes are limited by size. Their resolution depends on diameter. By linking telescopes worldwide, spanning continents, VLBI creates a virtual telescope as large as Earth. This technique has been crucial in capturing images of Sagittarius A's event horizon, including the black hole's shadow, providing insights into its structure. Recent inclusion of remote telescopes has significantly increased resolution, with the Event Horizon Telescope working toward clearer images of Sagittarius A after capturing the first black hole image in M87. Alongside VLBI, progress in millimeter and submillimeter wave technology has been critical. These wavelengths penetrate dense gas and dust near the galactic center, revealing accretion processes and matter dynamics. New, more sensitive receiver designs with lower noise allow detection of weaker signals previously obscured by cosmic background, resulting in more detailed images and spectra. These technological strides enable better understanding of the environment around Sagittarius A. Space observatories supplement ground-based efforts. Missions such as Chandra and the upcoming Athena X-ray satellite provide vital data on high-energy emissions near Sagittarius A. X-ray observations map heated regions of accretion flow and magnetic fields, offering clues about the processes near the black hole. Future missions aim for even greater sensitivity and spectral resolution, potentially unveiling detailed phenomena like accretion disk dynamics. Infrared telescopes, both ground and space-based, have become essential. Instruments like the VLT's gravity instrument use adaptive optics to correct atmospheric distortion in real time. This technology allows astronomers to accurately track stars orbiting Sagittarius A, determining the black hole's mass and influence with precision. Improvements in infrared detectors, with higher sensitivity and resolution, also help monitor transient events, providing insights into matter behavior under extreme gravity. Advances in computational power and data processing have been transformative. The volume of data from telescopes, sometimes petabytes, requires sophisticated algorithms. Machine learning and AI now help sift through this data, identifying patterns and anomalies that might be missed by humans. These tools refine models of accretion physics, jet formation, and magnetic fields, connecting observations with theoretical understanding. Specifically, interferometric data algorithms have improved image reconstruction quality, producing clearer, more accurate views of the galactic center. Software for phase calibration, atmospheric correction, and noise reduction enhances data fidelity, ensuring images are both visually striking and scientifically rigorous. These technological developments have unlocked long-standing enigmas about Sagittarius A. Increased temporal resolution allows near real-time observation of phenomena like flares, sudden brightenings caused by magnetic reconnection or plasma infall. Such data challenge existing models and inspire new theories about the interactions within the black hole's environment. Another exciting area is the development of quantum sensors and detectors, promising new ways to probe gravitational waves. These ripples in space-time, caused by massive objects like black holes, might soon be detectable from the galactic center, adding a new dimension to our understanding. Future missions and ground facilities are making strides toward that goal, which could reveal ongoing processes invisible in electromagnetic observations. Advances in computing have also enabled detailed simulations of accretion disks, jet formation, and magnetic field interactions. These models are calibrated against observations, testing our understanding of relativistic physics and exploring scenarios explaining observed phenomena like variability or jet emission. International collaboration and open data sharing platforms have been crucial. Repositories and coordinated networks let scientists worldwide analyze data from various wavelengths and techniques. This integrated approach provides a comprehensive view of Sagittarius A, combining electromagnetic, gravitational, and nuclear observations, fostering more nuanced insights into its complex behavior. All these advancements accelerate discovery, transforming Sagittarius A from a dark, mysterious spot into a vibrant environment full of activity we can observe in unprecedented detail. Each breakthrough in telescope design, detector sensitivity, computational analysis, or mission planning brings us closer to understanding how supermassive black holes influence galaxy evolution, their origins, and what they reveal about cosmic laws. The exploration of our galaxy's core is ongoing, but these tools are the best yet for illuminating the shadows cast by Sagittarius A. As technology continues to evolve, so will our understanding, opening new windows into one of the universe's most fascinating regions. Near Sagittarius A, the environment is a busy arena filled with objects that dance in the dark, driven by the immense gravity of the supermassive black hole. Stars are among the most obvious, their orbits mapped with precision over decades, revealing the black hole's hold on our galaxy's core. Some stars shine as brightly as our Sun, or even more, orbiting in tight, often elliptical paths, forming a celestial dance that provides vital clues about the dark mass at the center. The most famous star is S2, completing an orbit every 16 years. As S2 nears its closest approach, it accelerates to a significant fraction of the speed of light, over 2%. Observing S2's rapid motion and orbital shifts allows astronomers to measure the black hole's mass accurately, about 4 million times that of our Sun. Other stars share similar orbits, comprising the S-star population, each revealing more about the gravitational landscape of the galactic core. Stars are only part of the story. Beneath their bright surfaces lies a turbulent environment filled with gases and plasma. Clouds of hot gas swirl inward, heated to millions of degrees as they spiral towards Sagittarius A. This infalling matter doesn't plunge straight into the black hole but forms an accretion disk, a chaotic, flattened structure of gas and dust gradually spiraling inward. The process heats the gas, causing it to emit radiation across the electromagnetic spectrum, especially in X-ray and infrared wavelengths detected by telescopes. The gases near Sagittarius A are dynamic, influenced by tangled magnetic fields guiding jets of energetic particles that sometimes shoot out perpendicular to the accretion disk at nearly light speed. These jets are among the most spectacular phenomena near supermassive black holes, acting as beacons of activity and impacting regions thousands of light years away. They help astronomers understand matter behavior under extreme conditions as energetic particles interact with magnetic fields and ambient radiation. In addition to stars and gases, the region hosts compact objects, white dwarfs, neutron stars, and possibly smaller black holes that orbit the central mass. These remnants of earlier stars survive supernova explosions. Though less conspicuous, their presence can be inferred from gravitational effects or X-ray bursts when a neutron star accretes matter from a companion. The environment near Sagittarius A is also a place of episodic activity, showcasing the region's dynamic nature. Sometimes bright X-ray or infrared flashes occur, caused by sudden or explosive events, such as a star being torn apart when venturing too close, or a burst of increased accretion filling the region with energizing material. These phenomena demonstrate a constantly changing scene driven by interactions among stars, gas, and black holes. Dust clouds also populate this environment. While they can obscure views of the black hole in visible light, astronomers peer through infrared and radio waves to study the structure and composition of the interstellar medium in the galactic center. Some dust clouds are dense and cold, potential sites for star formation, despite the extreme conditions. Others are remnants of previous star-forming episodes, showing that this is a place of both destruction and creation. Object interactions shape this region significantly. When stars or gas clouds cross paths, gravitational interactions produce fascinating phenomena. Stars can be flung out at high velocities, becoming hypervelocity stars escaping the galaxy or tidally disrupted, contributing debris to accretion flows. Colliding gas clouds generate shock waves, heating and ionizing material, fueling the region's activity. These interactions help sculpt the environment, revealing how matter behaves under the influence of a supermassive black hole. The intense gravitational field near Sagittarius A subtly influences the orbits and life cycles of objects here. Small perturbations can alter trajectories over time, affecting the structure and density of the star cluster and the distribution of gas. This in turn influences how bright Sagittarius A appears across various wavelengths. The continual infall and ejection of matter shape the galaxy's evolution, with feedback mechanisms regulating black hole growth and the surrounding stellar population. Astronomers monitor these orbiting objects because they serve as natural probes of the black hole's properties. Tracking star and gas motions allows precise measurement of Sagittarius A's mass, confirming it as a black hole hundreds of millions of miles across but compressed into a point of extreme density. This computational detective work applies physics principles governing gravity and orbital mechanics, demonstrating how science can decipher the universe's dark mysteries. The interplay of stars, gases, dust, and remnants offers a window into matter's behavior under immense gravitational forces, helping us understand both the history and future of our galaxy. Gas accumulation feeds star formation in some regions, while black hole activity can suppress or trigger stellar births, creating a complex balance shaping the Milky Way's core over billions of years. All these objects and interactions form a vibrant, dynamic environment still being unraveled by scientists. Each new observation enhances our understanding of how supermassive black holes influence their surroundings and how these surroundings shape galaxy evolution. The orbiting stars, turbulent gases, and dusty clouds are part of a grand cosmic ballet around Sagittarius A, revealing the profound power and mystery within the heart of the Milky Way. Imagine the bustling center of our galaxy, a region teeming with stars, gas, and cosmic dust, all swirling in a complex gravitational dance. While black holes, especially supermassive ones like Sagittarius A, are invisible by nature, their gravitational pull exerts a profound influence on the cosmic neighborhood. Astronomers have devised ingenious ways to decipher their presence and size by carefully observing the paths stars trace around the galactic centre. The key lies in tracking the motions of stars that orbit close to Sagittarius A. These stars, sometimes only a few light-years away from the black hole, move at staggering speeds, completing orbits in times ranging from a few years to decades. By meticulously measuring their positions over time with high-powered telescopes equipped with adaptive optics, and employing infrared observations to cut through interstellar dust, scientists map out the precise trajectories of these stellar wanderers. Think of a star as a tiny planet orbiting an unseen, massive object. Its path is dictated solely by gravitational forces at play. If the star's orbit is highly elongated, it suggests a dominant central mass exerting a strong gravitational pull. Conversely, a more circular orbit indicates different dynamics. Analysing multiple stars with varying orbits allows astronomers to construct a detailed gravitational map of the galactic nucleus, revealing the presence of a compact, extremely dense object. But how do observations translate into a measure of mass? The answer involves applying the laws of physics, particularly Newtonian gravity, and in some cases, Einstein's theory of general relativity, to the observed orbital parameters. From the star's orbital data, such as radius, period, and velocity, scientists derive the mass enclosed within the star's orbit. This is often summarized by the classic equation: m volgeset frak volspjef 2 r yin, where m is the enclosed mass, vostverm the orbital velocity, rostiarm the orbital radius, and gm the gravitational constant. Imagine a star zipping around the galactic centre at a known velocity while orbiting at a known radius. Plugging these values into the equation yields the total mass within that orbit. Measuring several stars at different distances helps map how mass accumulates with radius. When the measurements show that an enormous amount of mass, millions of times that of our Sun, is confined within a tiny volume, it strongly suggests the presence of a supermassive black hole, rather than a cluster of dense stars or gas. One of the most compelling evidence comes from a star named S2, orbiting Sagittarius A in a highly elliptical path. Over decades, observations revealed that S2 completes an orbit roughly every 16 years, reaching speeds over 5% of light speed at closest approach. Such high velocities and tight orbits are impossible unless the central mass is incredibly concentrated and compact. Calculations indicate that within S2's closest approach, the mass enclosed is nearly 4 million times the Sun's, packed into a region roughly the size of our solar system. This total mass is so compact it defies any known configuration other than a black hole. No cluster of stars or dense gas sphere can maintain such a dense, massive, stable structure without collapsing or dispersing over cosmic timescales. Physics narrows the explanation to a black hole, leaving little room for alternatives. Additionally, astronomers analyse orbital motion using other techniques, like spectroscopy, which measures Doppler shifts in a star's light caused by its rapid motion towards or away from us. This method determines velocities with high precision, further refining mass estimates. Combining multiple observational methods ensures robust results. These measurements not only confirm the black hole's presence, but also help characterise it. The estimated mass provides a lower bound, while the absence of detectable emissions from Sagittarius A, despite its enormous mass, indicates it is relatively quiescent compared to active galactic nuclei. It's a supermassive black hole quietly influencing the galaxy's structure without overpowering brightness. The elegance of this approach is that it relies solely on gravity, the most fundamental force, allowing astronomers to see the unseen through its effects. Since black holes do not emit light directly beyond their event horizon, their presence is inferred mainly through nearby star motions. The star's orbits serve as reliable signposts, revealing a dense, dark mass in the galactic core. Looking ahead, advances like the gravity instrument on the Very Large Telescope Interferometer in Chile allow even more precise stellar motion measurements. These improvements can test Einstein's predictions in warped spacetime near Sagittarius A, bridging theoretical physics and observation. Studying stellar orbits will not only confirm the black hole's mass, but also reveal properties like spin and event horizon dynamics. Each star's path around the galaxy's centre is a cosmic heartbeat, telling a story of gravity's unyielding influence. By listening closely to these celestial whispers, scientists have painted a picture of an invisible giant, massive, dense, and mysterious, that governs the galaxy's heart. Through the analysis of stellar orbits, the black hole at Sagittarius A steps out of the shadows, not through light, but through stars' graceful dance in its grip. At the heart of our galaxy, the star S2 plays a crucial role in unveiling the mysteries of Sagittarius A. Imagine a celestial ballet, where S2's journey around the black hole is like a cosmic dance, revealing secrets that have challenged and expanded our understanding of the universe. Its orbit is not just beautiful, it is a powerful tool serving as a natural probe that allows astronomers to test the laws of physics under extreme conditions. S2 orbits the supermassive black hole at the galactic center at a breathtaking speed, approaching 90,000 miles per hour, completing a full orbit roughly every 16 years. Its periapsis, or closest approach, takes it within about 17 light hours of Sagittarius A, a remarkably tight distance considering the immense mass at the core. This proximity is key because it places S2 in a region where gravitational effects are intense, testing Einstein's general relativity. Why is S2 so important? Because its orbit provides direct, observable evidence of the black hole's gravitational pull. The star acts like a celestial test particle, orbiting the gravitational well carved out by the black hole, which weighs about 4 million times the Sun. Tracking S2's position over the years, astronomers observe how its speed changes, how its path bends, and how its orbit shifts, phenomena predicted by Einstein's equations. These measurements confirm the black hole's existence and enable precise estimation of its mass. Beyond confirming the black hole's presence, S2's orbit allows scientists to test general relativity in a regime of gravity far stronger than that on Earth. When S2 reaches periapsis, the gravity is so intense that light curves and shifts in wavelength due to gravitational redshift occur. Recent close approaches have revealed these effects, affirming Einstein's predictions in this extreme environment. The story of S2 isn't just about physics verification, it also helps us understand the galactic center environment. The star's orbit is influenced by a complex neighborhood, streams of gas, dust, and other stars swirling near Sagittarius A. Monitoring how S2's orbit responds to these influences, researchers learn about the distribution of matter, possible hidden objects, and the environment's overall structure. Its orbit also illuminates the nature of the black hole itself. S2's unwavering path provides clues about whether Sagittarius A is a classic Kerr black hole, as predicted by general relativity, or if there are deviations suggesting new physics. For example, scientists analyze orbital precession, the gradual shift of shape and orientation, to detect anomalies. So far, results align with Einstein's gravity, but each orbit adds confidence and occasionally surprises. Technological advancements have made tracking S2 possible. Instruments like the Very Large Telescope with adaptive optics have allowed astronomers to resolve S2's motion in detail. The Event Horizon Telescope, a global network of radio observatories, is set to produce even more detailed images as S2 nears periapsis. These twin technologies improve our ability to map S2's orbit and observe Sagittarius A's immediate environment, testing physics in real time. In recent years, as S2 approached its closest point to Sagittarius A, astronomers prepared for landmark measurements, capturing gravitational redshift and relativistic orbital precession. The anticipation was high because these signals verify key aspects of our physics models. When the data arrived, they matched Einstein's predictions with remarkable accuracy, reinforcing confidence in general relativity and marking a milestone. Yet each S2 orbit raises new questions. Is Sagittarius A truly a black hole, or could it be a more exotic object, such as a no-hair black hole or another form of compact mass? Might unseen companions, other stars, dark matter clumps, or stellar remnants affect S2's motion? Continued observations, especially during periapsis, are essential to probe these mysteries. Studying stars like S2 is crucial to understanding galaxy formation and evolution. Supermassive black holes influence their host galaxies, affecting star formation, gas flows, and dark matter distribution. Analyzing the orbits of stars around these giants offers insights into how galaxies grow and evolve over cosmic time. S2's story demonstrates how a single star can broaden our knowledge about the universe. Its orbit acts as a natural laboratory where fundamental physical laws are tested and validated. Every measurement, spectral shift, and subtle effect pushes the boundary of human understanding. Looking ahead, Ongoing and future observations will refine our knowledge. Precise measurements during upcoming periapsis passages may challenge existing theories or reveal subtle effects indicating new physics. The story of S2 isn't over. It remains a beacon, a cosmic Rosetta Stone for unlocking the universe's deepest secrets. In the grand cosmic dance, S2 reminds us how much we can learn from observing stars. Its orbit is a testament to human curiosity and ingenuity. Technological perseverance allows us to uncover the universe's fundamental mysteries. As we await the next close approach, each pass brings us closer to understanding the invisible giant at galactic centers. Near the very heart of our galaxy, the Milky Way, a dynamic and energetic environment unfolds constantly, driven by the immense gravity and interactions surrounding Sagittarius A. Among the most captivating phenomena are high-energy events like flares, sudden, intense bursts of radiation that can briefly outshine a million suns. These flares are more than spectacular displays. They provide vital clues about conditions near the supermassive black hole and the physics of extreme environments in the universe. Flares at the galactic center are primarily observed in X-ray and infrared wavelengths. They are characterized by rapid brightness increases, sometimes within minutes, followed by a gradual decline. These bursts are fleeting but occur frequently, making the region a hub of high-energy activity. Their recurring nature suggests an active, turbulent area, a cosmic storm in full swing. What processes might ignite these flares? One leading theory involves magnetic reconnection, familiar in solar physics, but happening on a vastly more energetic scale near the black hole. Imagine tangled magnetic fields twisting and pressing against each other until they suddenly snap and reconnect, releasing stored magnetic energy. This rapid process accelerates particles to near-light speeds, producing bursts of high-energy radiation observable as flares. Magnetic reconnection is crucial not only in the Sun's atmosphere, but also in the tumultuous vicinity of Sagittarius A. Another contributing process is matter accretion onto the black hole. Gas, dust, and stellar debris spiral inward, forming a turbulent, irregular accretion disk. Occasionally, chunks of matter or magnetic flux destabilize or divert, plunging toward the black hole. These infall events can generate shock waves, big energetic disturbances that heat plasma and release X-ray or infrared radiation. Such episodes might be triggered by instabilities in the accretion flow or collisions within the disk. Stars venturing close to Sagittarius A also contribute to high-energy activity. When a star or its planetary system drifts too near, tidal forces, powerful gravitational gradients, can tear stars apart or strip material, creating streams of debris. Some debris spirals inward, fueling increased activity and sometimes igniting flares. The frequent passage of these objects destabilizes the environment, leading to episodic feeding of the black hole. The surroundings become a chaotic zone, with streams of matter colliding and sparking radiation bursts detectable from Earth. The size and energy involved in these flares vary widely. They range from modest outbursts to extraordinary events releasing more energy in a few hours than the Sun does over hundreds of thousands of years. For example, some X-ray flares reach luminosities tens of times higher than Sagittarius A's steady emission. These energetic upheavals last from minutes to hours, with rapid rises and more gradual declines. The time profiles of flares provide clues to the physical size of the emission zones. Signals cannot travel faster than light, so the duration hints at the dimensions of the active region near the black hole. Infrared flares are similarly transient and are often correlated with X-ray bursts. They offer insights into the heating and dynamics of dust and plasma near the event horizon. Infrared observations reveal some flares originate from regions just a few times the size of our solar system around the black hole. These measurements help map the turbulent magnetized environment near Sagittarius A, where gravitational and electromagnetic forces clash in chaos. Theoretical models suggest that during these events, electrons can be accelerated to ultra-relativistic speeds. These high-energy electrons emit synchrotron radiation, light produced by charged particles gyrating around magnetic field lines, across a broad spectrum from radio waves to X-rays. Synchrotron emission explains much of the observed high-energy radiation associated with flares. Interestingly, some flares occur in rapid succession, known as flares cascades. Occasionally, a single flare is followed by smaller, repeated bursts, hinting at a complex sequence of magnetic reconnection or episodic matter inflows. Analysing the timing, energy, and spectral features of these flares helps researchers decode the choreography of particles and fields near the event horizon. Beyond understanding the environment around Sagittarius A Yum, these high-energy events serve as natural laboratories for extreme physics. Conditions near the black hole, temperatures of millions to billions of degrees, intense magnetic fields, and warped space-time are impossible to replicate on Earth. Flares act as probes into this realm, revealing how matter behaves under the universe's most extreme forces. Recent advances come from coordinated multi-wavelength campaigns, which combine observations from X-ray satellites, infrared telescopes, and radio observatories. These efforts have captured transient outbursts with unprecedented detail. By studying the timing, energy, and spectra of flares, astronomers seek to understand their triggers, whether primarily magnetic, gravitational, or a combination of processes. This remains an active area of research, with each flare offering a window into the dynamic core of our galaxy. Ultimately, the high-energy events near Sagittarius A depict a tumultuous environment in which matter and magnetic fields dance amid gravity and electromagnetic forces. These flares are cosmic fireworks, brief but brilliant, illuminating the mysteries of the universe's most extreme objects. They remind us of the immense, unseen energies lurking in the depths of our galaxy's core. The accretion of matter onto Sagittarius A, the supermassive black hole at the Milky Way's core, is a key process that influences its activity, yet remains a complex and partly mysterious phenomenon. To understand this influence, it's important to consider the galactic environment, the physics of accretion, and how variations in infalling material lead to observable changes in brightness, emissions, and outflows. At the galaxy's centre lies a dense setting with stars, gas clouds, dust, and stellar remnants, influenced gravitationally by Sagittarius A, which has a mass about 4 million times that of the Sun. Its enormous gravity extends beyond the event horizon, pulling in surrounding matter, gas clouds, stellar winds, debris, that form an accretion flow. Accretion onto Sagittarius A isn't straightforward. It involves gravitational attraction, angular momentum, magnetic fields, and turbulence. When gas or debris come close enough, they are pulled toward the black hole, but most orbit, forming an accretion disk, a rotating, flattened structure of hot plasma. This disk acts as a conveyor belt, causing matter to spiral inward, losing angular momentum and releasing gravitational energy as radiation. Within this disk, particles collide at high velocities, heating the plasma to millions of degrees and emitting high-energy radiation, mainly X-rays and infrared. Despite Sagittarius A's overall low luminosity, far quieter than active galactic nuclei, it still produces detectable emissions critical for understanding accretion physics, magnetic interactions, and black hole behavior. The low luminosity indicates a modest accretion rate, although even small increases in infalling matter can cause observable variations. One way accretion influences activity is through episodic flares. Occasionally, a gas cloud or dense region near the galactic center gets perturbed, perhaps by neighboring stars' gravity, and interacts with the environment. When this material is funneled toward the black hole, it temporarily boosts accretion, resulting in bursts of X-ray and infrared radiation. These flares, sometimes lasting from minutes to days, highlight the dynamic nature of accretion and provide insights into the mechanisms, like magnetic instabilities and turbulence, that trigger increased activity. Beyond radiation, accretion activity can also produce jets, narrow, high-speed outflows of charged particles ejected near the black hole's poles. Though Sagittarius A isn't as prominent as quasars, faint sporadic outflows have been detected. These jets are thought to originate from magnetic fields threading the accretion disk, which can channel some infalling material into outward jets at speeds approaching light. Such outflows influence surroundings by depositing energy into the interstellar medium, heating gas and dispersing dust, which can impact star formation nearby. The influence of accretion extends beyond immediate emissions. It shapes the galactic nucleus environment. As energy from accretion, radiation and outflows, heats surrounding gas, it can inhibit star formation by preventing gas clouds from collapsing under gravity, a process called feedback. Conversely, it can sometimes compress gas, triggering starbirth. This delicate balance affects the evolution of the galactic core and the growth of Sagittarius A over cosmic time. Sagittarius A's activity varies over time. While generally quiet, it sometimes enters heightened activity phases, often linked to variable accretion rates, due to passing gas clouds, stars, or transient magnetic phenomena within the disk. Observations show that even modest activity increases, such as X-ray flares and infrared brightening, are essential for probing low-luminosity accretion physics and the behaviour of the environment near the event horizon. The physics of accretion in this extreme regime involves understanding general relativity, plasma physics, and magnetohydrodynamics. Matter spiralling inward at relativistic speeds experiences intense gravitational forces, stretching and squeezing it, creating turbulent conditions. Magnetic fields, amplified and twisted by turbulence, are critical in transporting angular momentum, enabling matter to move inward while sometimes launching outflows. These processes are challenging to simulate but are fundamental to explaining how black holes grow and how their activity influences the galaxy. Advances through observations have enriched understanding. Space observatories like Chandra and XMM Newton have provided detailed X-ray images of Sagittarius A and its environment, revealing flare structures and the accretion flow's nature. Infrared telescopes like the Very Large Telescope help peer through dust and follow stellar and gas motions near the black hole. Radio arrays, including the Very Large Array and the Event Horizon Telescope, have achieved imaging of the black hole's shadow, directly visualizing the event horizon and surroundings. Combined, these multi-wavelength observations offer comprehensive insights into accretion dynamics. Future observations will deepen understanding further. Next-generation detectors and higher-resolution interferometry will enable real-time tracking of changes in accretion flow and jet activity. The Event Horizon Telescope's imaging of the black hole shadow already set a precedent. Ongoing efforts aim to observe near-horizon dynamics, shedding light on how matter transitions from turbulent disks onto the black hole. Studying Sagittarius A's variable activity and accretion is vital for understanding our galaxy's nucleus and the nature of supermassive black holes elsewhere. These phenomena serve as natural laboratories for testing gravity, plasma physics, and high-energy astrophysics. Moreover, understanding how a relatively quiescent supermassive black hole impacts its environment reveals insights into galactic evolution, star formation regulation, and black hole host galaxy coevolution. In short, the accretion of matter onto Sagittarius A is a complex process that influences activity levels through radiation, outflows, and feedback mechanisms shaping the galactic environment. Occasionally increased activity caused by the inflow of gas clouds or magnetic instabilities reveals the dynamic, energetic nature of the center. These processes exemplify the extreme physics governing supermassive black holes and serve as cosmic laboratories for fundamental laws. As our observational abilities grow, so will our understanding of the intimate relationship between accretion and activity, unraveling the mysteries at the galaxy's core. The supermassive black hole at the center of the Milky Way, Sagittarius A, is more than a silent cosmic giant. It plays a complex, dynamic role in shaping the galaxy's structure, evolution, and possibly its future. While often thought of as a cosmic vacuum cleaner, its influence extends far beyond swallowing matter, subtly moulding the galaxy in multiple ways. One primary way Sagittarius A affects the Milky Way is through regulating star formation in the galactic core. That region contains dense molecular clouds, gas, and dust, the ingredients for starbirth. However, the black hole's activity significantly influences these materials. During high accretion periods, when it consumes vast amounts of gas, energetic outbursts with jets and radiation heat, and disperse the surrounding interstellar medium. This process, called active galactic nucleus (AGN) feedback, can suppress star formation by preventing gas clouds from cooling and collapsing into new stars. Conversely, during quieter times, when Sagittarius AI accretes less, regions may cool enough to allow star formation to resume. This cycle of activity and calm means the black hole can turn star formation on and off in the galaxy's center. Over cosmic timescales, such regulation influences the distribution of stars and stellar densities, shaping the galaxy's inner morphology. This process helps determine whether the galaxy has a dense, bulge-dominated core or a more extended, less concentrated stellar assembly. Feedback from Sagittarius A can explain features such as the dense nuclear star cluster near the black hole and variations in young star populations in the core. Beyond star formation, Sagittarius A exerts gravitational influence that impacts the galaxy's overall shape. With a mass of around 4 million suns, it dominates the gravitational potential within the innermost few parsecs. This pull guides the orbits of stars, gas, and clusters near the centre. Over billions of years, gravity has sculpted this environment, funneling stars inward through complex dynamical processes. Stars orbit in elliptical orbits, some passing close to the black hole, others in elongated paths. These interactions lead to phenomena like angular momentum exchanges, causing stars to migrate inward or outward. Such migrations influence the central bulge's shape and density, contributing to the Milky Way's barred spiral structure. The nuclear star cluster, a dense spherical collection of stars surrounding Sagittarius A, partly results from these gravitational dynamics as stars are captured, scattered, or drawn into close orbits. The black hole's gravity also influences the galaxy's rotation pattern. Although it accounts for less than 1% of the galaxy's mass, it acts as a gravitational anchor around which stars, gas, and dark matter rotate. Rotation curves derived from star and gas velocities reveal this influence, especially near the centre, helping map the galaxy's mass distribution. This demonstrates that a supermassive black hole resides at the galaxy's core. The gravitational interactions also shape the galaxy's evolution, especially when satellites or star clusters collide or pass nearby. Sagittarius A's gravity helps capture or disrupt these structures. Some stars observed in the centre likely migrated from outside the galaxy, their orbits affected by the black hole. This process enriches the nuclear star cluster with diverse stellar populations and provides material for black hole growth through the capture of stellar debris or compact objects. Sagittarius A also influences the galaxy through energetic phenomena related to its variability. Although usually quiet compared to active galactic nuclei, it occasionally exhibits flares in X-ray and infrared light caused by sudden gas infalls or magnetic instabilities. These transient events energize the surrounding medium, producing shock waves and heating the environment. Such energetic outbursts can drive outflows of hot gas, observed as jets or winds. Though weaker than those seen in distant quasars, these outflows affect the nucleus and larger-scale gas dynamics. Over time, they can disperse gas reservoirs within the inner 100 light-years, influencing the formation of the galactic disk and spiral arms. Thus, the black hole's energetic activity impacts not just the core, but extends to the galaxy's broader structure. The black hole plays a central role in galactic feedback loops. Its activity interacts with the interstellar medium, regulating the growth of the galaxy's inner regions. This regulation helps shape the Milky Way into a spiral with a defined bulge, bar, and disk. The gravitational influence of Sagittarius A reinforces the barred spiral structure, involving resonances between the black hole's gravity and distributions of stars and dark matter. The galactic bar acts as a conveyor belt, funneling gas into the nucleus and fueling Sagittarius A, creating a feedback cycle that maintains the galaxy's architecture. Structures such as gas filaments, stellar streams, and orbital arrangements are heavily shaped by the combined gravity of the black hole and dark matter halo. These features reflect the galaxy's history of interactions, mergers, and dynamical evolution, all mediated by the central black hole. Its influence helps organize the galaxy's complex structures, playing a key role in shaping its long-term shape. In the cosmic dance, Sagittarius A acts as both conductor and composer. Its gravitational dominance orchestrates star and gas motions, guiding structure formation and sparking dynamic processes that ripple outward. Its episodic activity acts as a feedback mechanism, regulating star formation and generating large-scale outflows that influence the galaxy's halo and beyond. The black hole also influences the galaxy's future. During the anticipated collision with Andromeda in several billion years, Sagittarius A will be central to the merger. Gravitational forces will displace existing orbits, funnel matter inward, and likely trigger increased black hole activity. This upheaval could transform the galaxy into an elliptical or larger integrated spiral. Studying Sagittarius A offers key insights into galaxy formation and evolution. It shows how small, dense objects can create widespread effects, guiding galaxy assembly, shaping structures, and driving transformation. The interaction of gravity, energy feedback, and dynamic processes driven by the supermassive black hole reveal the complex forces that produce the Milky Way's distinctive form. In the universe's vast expanse, the black hole at the galaxy's center is more than an endpoint for matter. It's an active participant in a cosmic story. It links the microphysics of extreme environments to the macrocosm of galaxy evolution, demonstrating the interconnected nature of cosmic structures. Every star orbiting nearby, every gas cloud flickering with potential, and every spiral arm stretching outward is influenced by and connected to the silent, massive presence at the galaxy's heart. The question of whether Sagittarius A, the supermassive black hole at our galaxy's center, could affect our solar system in any measurable way is intriguing. It explores the connection between distant and nearby parts of the universe. Sagittarius A is over 26,000 light-years from Earth, mostly sitting quietly at the galaxy's core. Despite this distance, its immense gravity and energetic activity could, in principle, ripple through space and influence our solar neighborhood. Understanding supermassive black holes like Sagittarius A helps clarify this. These giants contain the mass of millions or billions of suns compressed into a tiny point. They exert a gravitational pull so strong that nothing, not even light, can escape once it crosses the event horizon. Outside that boundary, energy is released through accretion disks and relativistic jets, producing X-ray and infrared emissions that fluctuate with ingested matter. Despite these energetic displays, their influence diminishes significantly with distance from the core. Gravity follows an inverse square law, so its force lessens rapidly with distance. Although Sagittarius A is supermassive, its gravitational influence many thousands of light-years away is negligible compared to the gravity exerted by the Sun, planets, and local galactic environment. From our vantage point, the black hole's gravitational pull is minimal in affecting planetary motions or the stability of the solar system. Could activity from the black hole, like flares or jets, have a measurable effect? These energetic emissions are potent near the galactic center, but become vastly diluted over enormous distances. X-rays and high-energy radiation from flares travel at light speed, but are exceedingly faint by the time they reach us. The solar system is shielded from high-energy radiation by the gas, dust, and the Sun's magnetic field and atmosphere. Furthermore, the timing of Sagittarius A's activity is such that any bursts or flares originating at the galaxy's core would take thousands of years to reach us. Light from the galactic center takes about 26,000 years to arrive at Earth. If a flare occurs today, we won't see its effects for over 26,000 years. Conversely, if a flare happened 26,000 years ago, its radiation would just now be reaching us. This delay makes immediate, measurable influence impossible. Even hypothetically, if a massive object, like a neutron star or black hole, passed through the galactic core and generated a shockwave, the chances of such an event impacting our solar system directly are astronomically small. The galactic core is densely packed, but the probability of a direct collision or significant gravitational perturbation reaching us in any meaningful way is virtually non-existent. Some subtle effects over cosmic timescales are worth noting. Energy released by Sagittarius A influences the galactic environment, indirectly affecting the Milky Way's evolution. Feedback mechanisms like jets and energetic outbursts can regulate star formation, or influence the distribution of gas and dust. These processes change the galaxy's overall properties and demonstrate that despite its distance, the black hole plays a role in the galaxy's ecosystem, which our solar system orbits within. Models suggest the gravitational dynamics of the galaxy's core, partly influenced by Sagittarius A, affect the orbits of stars and gas clouds in the inner galaxy. Over long periods, these movements could have slowly altered the shape of the galactic disk or affected star clusters' paths. While these effects relate more to galactic structure than direct impacts on our solar system, they highlight the black hole's importance in the galaxy's gravitational framework. From a practical standpoint, the likelihood of Sagittarius A influencing our solar system, such as shifting planetary orbits, triggering cometary influxes, or causing mass extinctions, is effectively zero on human timescales. The immense distance, the attenuation of effects over that distance, and the dominant influence of the Sun's gravity mean such scenarios are impossible. Our planetary system is mainly governed by solar gravity and dynamics, with the galaxy serving as a distant backdrop. Scientists study Sagittarius A to understand black holes and the Milky Way's larger workings. Observing its flares and emissions offers insights into high-energy physics, gravitational interactions, and galactic evolution. While these observations help us understand our place in the universe, they do not imply that the black hole's activity has immediate effects on Earth or our solar system's stability. Overall, Sagittarius A is a vital part of the galaxy's structure, but its direct influence on our solar system is negligible. The vast distances, the laws of gravity, and physical laws ensure our solar system remains largely isolated from the galactic core. Our local environment, planets, and life on Earth are primarily shaped by the Sun's gravity and solar phenomena, with the galaxy acting more as a distant anchor than an immediate actor. Understanding Sagittarius A enriches our knowledge of cosmic processes, high-energy physics, and galactic dynamics. It reminds us that even the universe's most massive objects are governed by distance and natural laws, limiting their immediate impact. The black hole's role is more about shaping the galaxy than directly affecting Earth, highlighting the universe's vast and subtle forces that preserve the stability of our local space. While Sagittarius A symbolizes the universe's grandeur and the mysterious nature of black holes, its effects are mostly indirect and minimal on human timescales. The universe's physical laws and immense distance intervene, protecting our solar system from the tumult at the galactic center. Studying such phenomena expands our understanding of the universe's intricate web, illustrating that even the mightiest objects abide by the constraints of distance and physics, ensuring our solar system's safety amid cosmic scales. The role of Sagittarius A in star formation and galactic evolution is profound and complex, stretching across millions of years and influencing the fabric of the Milky Way. At the galaxy's core, this supermassive black hole is often seen as a voracious consumer of matter, but its impact extends far beyond that. It acts as both regulator and catalyst, shaping its surroundings in ways that ripple through the galaxy. Starting with star formation, the regions around Sagittarius A are densely packed with gas, dust, and energetic particles. These swirling clouds serve as raw materials for starbirth, but their evolution from diffuse clouds to shining stars is complicated. The black hole's activity significantly affects this process. When accreting matter, Sagittarius A emits bright X-ray and infrared radiation, injecting energy into the interstellar medium. This radiation heats nearby gas clouds, increasing their temperature and pressure. Heating can prevent gas from collapsing under gravity, effectively suppressing star formation in some regions. It acts as a cosmic thermostat, controlling starbirth and maintaining galactic balance. Conversely, black hole outbursts and jets during episodes of high activity, known as active galactic nucleus phenomena, can compress gas farther away. This compression can trigger star formation by squeezing gas clouds past the collapse threshold. Imagine the black hole as a cosmic gardener, pruning and fertilizing the galactic environment, fostering some star formation while restraining others. Sagittarius A influences not only local regions but also wider galactic evolution through feedback mechanisms. When the black hole's accretion accelerates, jets and winds launched into space can clear out large gas regions, sometimes halting star formation by removing raw materials. Conversely, energetic outflows can induce turbulence and instabilities in the interstellar medium, fostering starbirth in some circumstances. Essentially, the black hole acts both as a sculptor and a moderator, carving zones of activity and lull that influence the galaxy's large-scale structure. On larger scales, Sagittarius A plays a key role in the evolution of the galactic core. Its growth history is tied to the formation and movement of star clusters and molecular clouds. Processes feeding the black hole, such as gas infale and interactions with orbiting stars, affect the distribution of mass and momentum in the central region. Over cosmic times, these interactions influence the shape and density of the galactic bulge, contributing to the Milky Way's overall morphological evolution. The black hole's influence on galactic evolution mainly operates through feedback loops, processes regulating matter and energy flow. In galaxy formation's early stages, Sagittarius A may have been more active, powering quasars and active nuclei that shape their host galaxy's growth. Although currently relatively quiet, sporadic episodes of activity still influence the Milky Way's evolution. These feedback processes help explain why some galaxies have massive, dense cores with advanced stellar populations, whereas others are more diffuse. Furthermore, the black hole affects star dynamics. Stars orbit close to Sagittarius A, follow paths dictated by its immense gravity. Studying these orbits provides strong evidence for the black hole's existence and reveals insights into its mass and nature. These stellar motions trace the gravitational landscape, shaping our understanding of dark matter and baryonic matter distribution in the galaxy. The impact of Sagittarius A extends beyond our galaxy. It serves as a laboratory for understanding extreme gravity, magnetic fields, and high-energy particle acceleration. Insights from Sagittarius A help astrophysicists explore galaxy life cycle processes and the coevolution of black holes and their hosts, a relationship reflected in correlations between black hole mass and properties of the galactic bulge, like luminosity and stellar velocity dispersion. An intriguing aspect is the interplay between galactic mergers and black hole activity. When galaxies collide and merge, a common cosmic event, the central black holes likely interact and eventually coalesce, releasing massive energy. These cataclysmic events can spark intense black hole feeding episodes, influencing star formation and galactic structure. Although the Milky Way is relatively quiescent now, evidence suggests it experienced more tumultuous times, with Sagittarius A playing a central role during periods of heightened activity. Ultimately, Sagittarius A is much more than a silent sink. It actively participates in the galaxy's growth and transformation. Its gravity shapes stellar orbits and guides gas cloud motions, while energetic outbursts modulate star formation conditions in the galactic nucleus. Feedback mechanisms regulate molecular gas reservoirs, balancing growth and suppression. As astronomers peer deeper into the galactic center, they unveil the intricate dance between black hole and galaxy, a dance unchanged for billions of years and likely to continue. In the broader cosmos, Sagittarius A exemplifies the power of supermassive black holes. Though often invisible and silent, its influence underpins the structure and evolution of the Milky Way, shaping countless stars, nebulas, and planets, including Earth. It stands as a silent giant at the galaxy's core. Its gravitational pull and sporadic energy releases sculpting the universe in subtle and spectacular ways. As scientists continue to unravel the mysteries surrounding Sagittarius A, the potential impacts of future encounters with our galaxy's central supermassive black hole become both fascinating and significant. From our vantage point, Sagittarius A appears quiet and inscrutable most of the time, but the universe is unpredictable, and future interactions could ripple through the galaxy in subtle and dramatic ways. One immediate impact could come from bursts of energy emitted during episodes of increased accretion activity. When clouds of gas and dust drift too close or become destabilized and funnel into Sagittarius A, they can ignite energetic outbursts, flares of X-rays and infrared radiation traveling at the speed of light. These bursts not only shine brightly, but can influence surrounding environments, bathing the central regions in high-energy radiation and interacting with galaxy-wide magnetic fields. Over time, repeated energetic events might influence star formation rates in the galactic core, either by compressing gas clouds to spark new stars or dispersing matter to inhibit star formation. A significant way future interactions could reshape the galaxy involves black hole feedback mechanisms, powerful outflows such as jets and winds extending over countless light years. While Sagittarius A is relatively quiet now, gravitational interactions with passing stars, compact objects, or dense molecular clouds may excite its activity. An active black hole can generate jets that carve out cavities in the interstellar medium, dispersing gas and dust and regulating star growth in the nucleus. If Sagittarius A becomes more active or experiences an energetic outburst, it could stir the galactic core, redistributing matter and altering star formation, influencing the Milky Way's overall architecture. On larger scales, future interactions might also influence the galaxy's dynamical structure. Sagittarius A's gravitational influence extends beyond its immediate vicinity, shaping the orbits of stars and clusters near the core. Sudden changes in activity or a shift in mass distribution, possibly due to the infall of mass from a gas cloud or a small galaxy, could subtly tweak stellar orbits over millions of years. Such shifts might impact the core's stability, influencing star and gas distribution and the galaxy's evolution. Contemplating more dramatic, speculative scenarios raises interesting possibilities. If Sagittarius A were to consume a massive object, like a dense star or dwarf galaxy, The energy released could be enormous. The surge in radiation and particles might impact the galaxy significantly. High-energy particles could alter the interstellar medium far beyond the core, influence cosmic ray fluxes, and potentially affect planetary systems even in the spiral arms where stars such as our Sun reside. Although these events are rare and unpredictable, they serve as reminders of the dynamic, sometimes volatile, environment around supermassive black holes. Beyond astrophysical impacts, there are philosophical and practical dimensions. As humanity advances technologically, future observations or direct interactions, such as deployment of probes or daring space missions, could deepen our understanding of black hole physics. Such exploration might yield insights into fundamental laws governing gravity, quantum mechanics, and extreme conditions. Our future engagement with Sagittarius A could stimulate technological innovations, foster scientific curiosity, and expand our comprehension of the universe's history and future. Understanding how supermassive black holes influence their host galaxies also informs broader cosmology. Similar processes are thought to occur in other galaxies, some with more active or larger black holes. Studying Sagittarius A offers clues about the evolution of the universe, as galaxy formation and growth are intertwined with black hole development. The interplay between accretion activity, feedback mechanisms, and stellar dynamics shapes the cosmic landscape, influencing the growth and structure of galaxies. Looking ahead, future interactions with Sagittarius A may challenge our current understanding of physics. The extreme gravity and magnetism near the event horizon push the limits of Einstein's general theory of relativity. Observing unexpected flares, jets, or phenomena could prompt refinements of current theories or suggest new physics. Ultimately, our relationship isn't just about distant observation, but about actively contributing to uncovering the universe's fundamental laws. Each encounter with Sagittarius A, whether a brief flare or prolonged activity, has the potential to influence the galaxy subtly or profoundly. These interactions could alter matter flow at the core, reshape star formation patterns, or redefine the galaxy's structure over cosmic time. As observation techniques improve and models become refined, we will gain clearer insights into how this unseen giant continually shapes our galaxy. The more we learn, the more we realize that our galaxy's story is entwined with the quiet, powerful influence of the universe's ultimate gravitational anchor. These future interactions, whether energetic flares, outbursts, or shifts in activity, illustrate the dynamic nature of cosmic environments centered around supermassive black holes. Understanding these processes is vital as they influence star formation, galactic architecture, and the universe's broader evolution. As observations improve, we may uncover surprises that challenge current theories, pushing physics toward new discoveries. The potential for future encounters offers a glimpse into the interconnectedness of cosmic phenomena. Sagittarius A is more than a distant, inscrutable object. It is a central driver of the Milky Way's evolution. By studying its behavior and impacts, scientists aim to decode complex interactions shaping galaxies. These insights deepen our understanding of how galaxies grow and evolve, and how supermassive black holes influence the universe. As technology advances, our ability to observe and interact with Sagittarius A will improve, opening new doors. Missions close to the black hole or instruments capturing phenomena in unprecedented detail could revolutionize astrophysics. Such efforts might reveal new physical processes, deepen understanding of gravity, and offer insights into the earliest universe moments. In conclusion, each interaction with Sagittarius A, from minor flares to major activity, may influence our galaxy in meaningful ways. These events could shift star orbits, alter star formation, or reshape the core's structure. Continued technological progress and theoretical refinement will enhance our grasp of how this invisible giant shapes the Milky Way. Our growing knowledge highlights the profound link between the black hole at the galaxy's center and the cosmic environment it influences, shaping the galaxy's story over cosmic timescales. Understanding the future behavior of Sagittarius A involves combining theoretical models and observational data to forecast its activity over various timescales. These models serve as cosmic maps, outlining possible paths of this supermassive black hole and its influence on the galaxy. Magnetohydrodynamic (MHD) simulations are central to this effort. They combine magnetism, fluid dynamics, and gravity to recreate the environment near Sagittarius A. These simulations visualize gas and dust spiraling inward, forming accretion disks with magnetic fields causing instabilities that lead to flaring activity. By inputting variables such as black hole mass, properties of surrounding matter, and initial magnetic configurations, these models project how accretion flows evolve, highlighting potential periods of increased activity or quiescence. Refined over years and informed by observations tracking X-ray and infrared emissions, MHD simulations have successfully predicted events like the passage of gas clouds such as G2 near Sagittarius A. They forecasted a spike in accretion, later confirmed by telescopes, validating their predictive capability. As new gas clouds or stellar debris approach the galactic center, these simulations remain vital tools for forecasting future activity. Magnetic reconnection models focus on events where magnetic field lines snap and realign, releasing energy in brief bursts. Simulations of reconnection help predict the timing and strength of flares, suggesting the environment often approaches magnetic instability. Periodic reconnection may trigger sudden radiation outbursts affecting observed activity. Monitoring magnetic field strength and configuration helps estimate when reconnection-driven flares might occur. Models examining large-scale gravitational influences also contribute to predictions. They analyze how stars and stellar remnants gravitationally interact, potentially perturbing accretion flow or causing fluctuations in matter inflow. As stars orbit, their gravitational tugs can nudge gas clouds inward, leading to episodic feeding. Tracking stellar motions allows anticipation of increased inflow periods, indicating potential heightened activity. Relativistic ray tracing models, grounded in Einstein's general relativity, simulate how light escapes warped space-time around the black hole. These models predict changes in the appearance of the black hole's shadow and surrounding accretion flow during energetic events like flares or jets. Visual predictions from these models guide observational campaigns, helping astronomers schedule studies during predicted high-activity periods and monitor transient phenomena effectively. The long-term evolution of Sagittarius A depends heavily on its accretion rate, the matter falling into the black hole over time. Activity levels could fluctuate widely depending on the gas and dust supply. If the central gas reservoir depletes, the black hole might enter a quiet, prolonged phase. Conversely, ongoing stellar winds and infalling gas clouds likely sustain a baseline activity punctuated by occasional flares. These variations influence not only the black hole's evolution, but also nearby star formation and overall galactic development. Feedback mechanisms are modeled to understand Sagittarius A's influence on its surroundings. Active accretion episodes can produce jets, powerful streams of charged particles traveling near light speed that deposit energy into the interstellar medium. These jets heat surrounding gas, possibly suppressing or triggering star formation, which in turn affects the fuel supply for the black hole. Predicting the timing and strength of jets requires understanding complex interactions among magnetic, accretion, and relativistic physics. Advancements in computational astrophysics promise more refined models. Machine learning algorithms trained on extensive observational datasets help identify subtle patterns indicating upcoming activity. When combined with high-resolution observations from facilities like the Event Horizon Telescope and future missions, these models will improve in accuracy and predictive power. Collectively, these models portray Sagittarius A as a dynamic entity, not solely a tranquil, invisible giant, but an active cosmic actor driven by gravitational, magnetic, and hydrodynamical processes. By integrating simulation results with observational data, scientists continually enhance their ability to forecast its behavior. This ongoing refinement offers insights into how our galaxy's central engine might evolve over the coming millennia. Despite remarkable progress, many mysteries about Sagittarius A still linger, beckoning us to explore deeper into our galaxy's core. These enigmas challenge current theories and inspire new inquiries, pushing technology and understanding to their limits. One of the most tantalizing questions concerns the nature of Sagittarius A's activity. It can light up suddenly with powerful flares, temporarily outshining many luminous objects. These energetic outbursts seem connected to accretion episodes, when gas and dust spiral into the black hole, but the mechanisms behind these surges remain elusive. Are they caused by magnetic reconnections, similar to solar flares, or do instabilities within the accretion disk trigger them? Understanding what sparks these eruptions could reveal much about black hole feeding processes, magnetic fields, and plasma behavior under extreme gravity. Another mystery involves the structure of the accretion flow. Is Sagittarius A surrounded by a thin, well-defined disk, or does it host a chaotic, inefficient flow? The flow's geometry influences how matter interacts with the black hole, affecting its growth and emitted signals. Observations suggest that the accretion might be radiatively inefficient, meaning most energy is swallowed or expelled in ways not yet fully understood. Clarifying this structure would shed light on how supermassive black holes feed and influence their environments, especially in low luminosity regions like our galactic center. Linked closely is the influence of Sagittarius A on its surroundings. Although black holes are often seen as destructive, they also play roles in galaxy evolution. The extent of feedback, energy and particles impacting gas and star formation is still poorly understood. Does Sagittarius A regulate star formation in the galactic core? Do jets and outflows carry enough energy to heat or expel gas, affecting star creation? Understanding this feedback loop is crucial because it connects black hole physics to the broader evolution of galaxies. The stellar population orbiting Sagittarius A raises additional questions. Over decades, astronomers have tracked stars in tight elliptical orbits, revealing the black hole's tremendous gravity. Yet, some stars appear young and massive, which challenges theories of star formation there. The harsh environment, strong radiation, gravity, and turbulent gas makes in situ formation difficult. How did these stars form? Were they born in a dense gas disk or migrated inward? Deciphering their origins helps unravel how stars can form under extreme conditions and how black holes shape their stellar neighborhoods. A profound mystery concerns the fundamental nature of the black hole itself. According to Einstein's general theory of relativity, Sagittarius A should have an event horizon from which nothing escapes. But are there quirks suggesting new physics? Might the black hole have features that challenge our gravity or quantum mechanics? Some theories propose quantum structures at the horizon, or exotic objects mimicking black holes but differing fundamentally. These ideas, while speculative, push the frontiers of physics. Upcoming observations of matter and light near the event horizon could test these theories and reveal whether black holes are as classical as described, or if new physics lies just beyond. The black hole's spin remains uncertain. Spin influences how matter accretes and how jets form. Determining if Sagittarius A spins rapidly or slowly can illuminate its growth history, whether it accrued mass steadily or through mergers. Measuring spin involves analysing subtle signals in emitted radiation, a challenge amid nearby complex environments. Unlocking this parameter will help reconstruct the black hole's past and clarify the evolution of supermassive black holes across cosmic time. Another enduring mystery is whether Sagittarius A is the endpoint of gravitational collapse, or if quantum physics prevents a true singularity. Some propose a quantum gravity cutoff, preventing singularity formation and creating ultra-dense exotic states or remnants. These ideas, though speculative, challenge our understanding of spacetime and the classical paradigm of black holes. Observations near the event horizon might someday reveal clues about the nature of these objects, indicating whether they are purely classical predictions or if new physics exists beyond our current reach. The long-term evolution of Sagittarius A also sparks curiosity. Will it stay quiet or enter phases of heightened activity like distant quasars? Will it grow significantly by consuming more mass, or will feedback processes limit its growth? These outcomes depend on complex variables: galactic dynamics, gas supply, magnetic fields. As models improve and data accumulates, we hope to anticipate the future of this unseen giant. These mysteries highlight how much remains unknown about Sagittarius A. Each question leads to new insights about fundamental physics, galaxy evolution, and the universe's nature. As technology advances, more sensitive telescopes, interferometers, and models, we approach unlocking these cosmic secrets. Sagittarius A persists as a silent gravitational anchor and a gateway to understanding extreme phenomena, from black hole physics to galaxy evolution. It challenges our theories and invites us to explore the cosmos's most mysterious realms, inspiring both curiosity and scientific progress. Dark matter plays a crucial role in shaping the dynamics at the galactic center, especially around Sagittarius A. the supermassive black hole at our galaxy's heart. Although it does not emit, absorb or reflect light, dark matter's gravitational influence is fundamental in binding the universe and guiding the motions of stars and gas near the core. Envision the galaxy as a vast, swirling city of stars, gas, and dust, held together by an invisible dark matter halo extending well beyond luminous matter. This halo acts as a gravitational scaffold, anchoring the galaxy and surpassing visible structures. Near Sagittarius A, dark matter's influence is subtle but significant, contributing to the gravitational potential that shapes the motions of stars, gas, and dust around the core. It helps explain the orbital paths of stars close to the black hole, which are measured with increasing precision. Precise measurements of stellar orbits reveal Sagittarius A's dominant gravitational pull. To understand these motions, astronomers must consider the gravitational pull of both visible and dark matter. Dark matter forms an invisible cocoon around the galaxy's center, subtly affecting the trajectories of stars and the distribution of matter. It acts like a hidden hand, keeping stars at the outskirts of the core bound within the galaxy and maintaining its long-term stability. Dark matter's gravitational presence also influences matter accreting onto Sagittarius A. Gas and dust spiraling inward are shaped by the combined pull of visible matter and dark matter. While the black hole dominates its immediate vicinity, the broader dark matter distribution provides the gravitational landscape, guiding larger-scale accretion flows. This landscape is vital in feeding the black hole over cosmic timescales. Its influence extends beyond guidance. Dark matter has shaped galaxy evolution by forming dense halos during its formation billions of years ago. These halos provided gravitational wells into which normal matter fell, cooled, and condensed into stars, shaping the galaxy's structure. The dark matter halo determined where this process occurred, affecting the central region's formation and the assembly of luminous matter. Some theories propose dark matter may weakly interact with regular matter, influencing gas and particle behavior at the galactic center. While direct detection remains elusive, understanding its gravitational effects constrains models and helps us understand possible dark and normal matter interactions. These insights are critical for learning about dark matter's fundamental properties. Near Sagittarius A, dark matter density is believed to increase, forming a dark matter spike due to the black hole's gravitational pull, drawing dark matter inward over time. Although current observations are limited, simulations suggest this spike could enhance the local gravitational influence, subtly affecting stellar and gas motions. It might influence the rate at which Sagittarius A accretes matter or produce observable effects on stellar orbits. Understanding dark matter's role has implications beyond galaxy formation. It addresses fundamental questions about the universe. Studying how dark matter influences the galactic center may help unveil its nature, whether composed of weakly interacting particles, ultralight bosons, or other entities. The behavior of dark matter around Sagittarius A could shed light on physics beyond current theories, offering insights into the universe's fundamental nature. Throughout galaxy evolution, the interplay between visible matter, dark matter, and the central black hole has shaped cosmic history. Mergers, interactions with dark matter subhalos, and internal dynamical processes contribute to this evolution. When galaxies merge, dark matter halos often combine before luminous matter, setting the stage for new star formation and black hole activity. These events reshape dark matter distribution, altering Sagittarius A's gravitational landscape. Scientists use simulations to understand how dark matter influences supermassive black hole formation and growth. Some models suggest dark matter acts as a reservoir, slowly supplying material into the galaxy's core to feed Sagittarius A. Others propose fluctuations in dark matter density trigger episodic feeding events, causing flares or jets from the black hole. While much remains theoretical, evidence confirms dark matter's gravitational influence is vital when studying the galactic center. The orbits of stars near Sagittarius A, especially close companions, serve as sensitive probes of dark matter's presence. Deviations from expected trajectories based solely on visible matter hint at dark matter's distribution. Future telescopes and more precise measurements will help peel back cosmic layers, revealing how dark matter's unseen mass influences the galaxy's core dynamics. As understanding advances, researchers aim to resolve deeper questions. How do galaxies grow and evolve? What is dark matter's true nature? How does this mysterious component influence the universe? Each insight draws us closer to answering these fundamental questions, revealing unseen forces that have shaped the cosmos for billions of years. In the galaxy's core, Sagittarius A quietly dominates its chaos, but dark matter continues its silent work. Its gravitational influence shapes stellar motions, feeds the black hole, and supports the galaxy's structure in subtle yet profound ways. Unlocking dark matter's secrets promises deeper understanding of our galaxy and fundamental insights into the cosmos. The universe is filled with mysteries, especially in the hearts of galaxies where supermassive black holes reside. For decades, astrophysicists have studied these giants, but their origins and nature remain debated. One major question is how they form. Are they born from the direct collapse of primordial gas clouds, creating black holes with millions of solar masses, or do they grow over time by merging stellar mass black holes and accreting gas? Many researchers suggest a combined process. In the early universe, some black holes form rapidly, providing seeds for later growth. As galaxies collide, their black holes are believed to merge, forming larger supermassive black holes. But questions persist about how quickly these processes occur, especially given the existence of quasars, luminous objects powered by supermassive black holes, less than 1 billion years after the Big Bang. How did these black holes grow so fast? Were their seeds unusually massive, or was accretion highly efficient? Debates also focus on how supermassive black holes are fed. The accretion process involves extended disks of material emitting radiation across the spectrum. Some astrophysicists argue black holes grow mainly through steady, gradual accretion of gas and dust. Others propose that dramatic events like galaxy mergers cause rapid inflows of material, igniting active galactic nuclei and boosting black hole mass quickly. This leads to questions about growth regulation. How do black holes avoid uncontrolled growth? Feedback processes, where radiation, jets, and winds from the accretion disk exert pressure, may regulate material inflow. These processes not only influence black hole growth, but also impact star formation within the host galaxy, leading to coevolution models. Researchers are actively debating the effectiveness of these feedback mechanisms and their role in shaping the galaxy-black hole relationship. Another ongoing debate concerns the observed correlations between black hole mass and galaxy properties, such as the Sgr A relation, linking black hole mass to the stellar velocity dispersion in the galaxy's bulge. This suggests a fundamental connection. But is this causative? Do black holes influence galaxy evolution through feedback? Or is it an indirect result of shared merger and star formation histories? Some scientists think the correlation arises from shared evolutionary processes rather than direct regulation by black holes. The nature of the regions surrounding black holes also fuels debate. The event horizon, telescopes' images of Sagittarius A's shadow have garnered attention, but they raise questions about the structure of the event horizon and matter behavior near it. Does the data support the classical black hole model, or could alternative concepts such as horizonless objects or fuzzballs better explain observations? While most favour the black hole paradigm, these questions challenge Einstein's general relativity and open the possibility of new physics near the horizon. Gravitational wave observatories have added data by analysing signals from black hole mergers, probing the behaviour of space-time in extreme conditions. The black hole information paradox, a question of whether information swallowed by black holes is lost or preserved, is another controversial issue. Some propose that information is retained holographically on the black hole's boundary, while others suggest unknown quantum processes could erase it. Resolving this paradox could revolutionise our understanding of physics, uniting quantum mechanics and gravity. Black holes also influence the broader universe. Are they mere byproducts of galaxy formation, or do they actively shape large-scale structure? Some view supermassive black holes as cosmic engines, driving galaxy evolution through jets and radiation. Others see them as relics, fossils reflecting early universe conditions, not active agents of change. Their role in cosmic reionization is also debated. While stars and smaller black holes contributed to reionization, the impact of early supermassive black holes remains uncertain. Did they significantly ionize the intergalactic medium, or were their effects localized? These mysteries underscore how little we know. Every discovery, every debate driven by new data, reveals gaps in our understanding of these entities. Supermassive black holes at galaxy centers are more than objects of fascination. They're essential to understanding the universe's history and structure. Advances in technology, next-generation telescopes and gravitational wave detectors may broaden our knowledge, but current debates keep scientists questioning and refining their models. The formation and growth mechanisms, feeding processes, feedback regulation, and their connection to galaxy evolution continue to be active research areas. Future observations will likely provide more clarity, but for now, these questions stimulate ongoing scientific inquiry. Each challenge invites a deeper look into how these enigmatic giants influence their surroundings and the cosmos at large. The story of supermassive black holes remains a frontier, promising new insights into fundamental physics and the universe's earliest epochs. As data accumulates, our understanding will evolve, but the mysteries they hold ensure that the debate will continue, engaging astrophysicists in the quest to unravel one of the universe's most profound secrets. Looking ahead, the universe's most mysterious heart, the region surrounding Sagittarius A, is set to reveal more secrets thanks to ambitious projects and missions. These endeavours aim to enhance our view of the black hole's environment, deepen our understanding of the processes involved, and challenge current physics. One of the most anticipated is the Next Generation Event Horizon Telescope, EHT. Building on the success of the first array that produced the iconic image of the black hole in M87, the EHT is expanding and upgrading. The improved network will achieve higher resolutions, allowing scientists to peer closer to Sagittarius A's event horizon with unprecedented detail. By capturing sharper shadows and features of the accretion flow, these observations will help us understand matter spiraling into the black hole, jet formation, and electromagnetic field interactions in extreme environments. Enhanced detectors and wider frequency coverage will enable mapping of the turbulent plasma with remarkable precision. Complementing the EHT's improvements are space-based observatories surveying the galactic center at different wavelengths. The James Webb Space Telescope, JWST, still in early science phases, offers a powerful infrared view penetrating dense dust clouds obscuring the core. Its sensitivity allows tracking star motions and compositions near Sagittarius A, revealing the black hole's gravitational influence on stellar orbits with new clarity. This informs us about the evolution of the galactic nucleus and how it shapes the galaxy's history. Another upcoming mission is the European Space Agency's Athena, Advanced Telescope for High-Energy Astrophysics, a leap forward in X-ray astronomy. When launched, Athena will scrutinize energetic phenomena near black holes, including accretion disks and ultra-fast outflows. By capturing high-resolution X-ray spectra, scientists aim to decode the physics of matter plunging into Sagittarius A, shedding light on how black holes generate radiation and jets. These insights could explain the mechanisms behind energetic flares, revealing how the black hole accretes matter. LISA, the Laser Interferometer Space Antenna, scheduled for launch within the next decade, is a space-based gravitational wave observatory. LISA will detect ripples from massive objects, including signals from the inspiral and merger of intermediate mass black holes, or stars falling into Sagittarius A. These gravitational waves will open a new window into the black hole's surroundings, providing insights into its mass, spin, and history, as well as the dynamics of nearby stars. Ground-based projects aim to push radio astronomy forward. The Very Large Array, VLA, continues upgrades to improve sensitivity and resolution. The Square Kilometre Array, SKA, under construction in Australia and South Africa, will be the world's largest and most sensitive radio observatory once operational. It will monitor radiation from hot plasma near Sagittarius A, and reflections from jets and outflows. Its extensive collecting area will enable detailed timing, revealing how the black hole responds to accretion events and magnetic phenomena, helping us understand its role in galactic feedback, how active black holes influence their host galaxies. Time domain surveys also hold promise. The Vera C. Rubin Observatory, formerly LSST, will conduct rapid, wide-field sky surveys, capturing transient phenomena like energetic flares or tidal disruption events, stars torn apart by the black hole's gravity. Quick alerts will enable follow-ups across multiple wavelengths, offering comprehensive views of these events. This will help us understand how Sagittarius A varies and the mechanisms behind its flickering activity. Developments in high-energy particle detection, such as the Cherenkov Telescope Array We'll also refine our understanding of energetic processes near the black hole. These observatories detect gamma rays produced in high-energy interactions, helping map how particles accelerate to near-light speeds around Sagittarius A. Observing these phenomena over time will elucidate how black holes influence their surroundings through gravity, electromagnetic radiation, and cosmic ray acceleration. The technology behind these projects involves more than bigger telescopes or better detectors. Advancements in data processing, computational modeling, and simulations are increasingly vital. Artificial intelligence and machine learning algorithms are essential for managing large data streams, identifying patterns, predicting activity, and filling observational gaps. These tools improve our ability to interpret complex signals, develop accurate models, and enhance our understanding of the black hole's behavior. These projects are not just about gathering data, they will generate new questions. How does Sagittarius AI grow and evolve? What physical limits govern its activity? How does it influence star formation and galaxy evolution over cosmic timescales? As instrumentation improves and exploration advances, each discovery will deepen our understanding of the fundamental laws of the universe. This era of exploration promises to transform Sagittarius A from a mysterious, invisible mass into a dynamic, well-characterized engine of cosmic activity. In our lifetimes, new observations could unveil details that have eluded astronomers for decades, shaping our perception of the universe's most extreme phenomena. The possibilities are as vast as the galaxy itself, encouraging us to decode the enigmatic behavior at the galaxy's core. Studying Sagittarius A offers vital insights into the universe's most extreme environments. As a supermassive black hole roughly 4 million times the Sun's mass, it serves as a natural laboratory for understanding gravity, matter, and energy under conditions impossible to replicate on Earth. Observing its behavior allows scientists to test Einstein's general relativity and explore physics beyond current models. Sagittarius A influences the Milky Way structure significantly. Its gravitational pull affects the orbits of stars near the galactic core, requiring detailed mapping of these motions. Tracking these orbits enables astronomers to determine the black hole's mass precisely and refine our understanding of supermassive black holes across the universe. These stellar movements provide direct evidence of the black hole's existence and insights into how such giants form and evolve over cosmic time. Additionally, Sagittarius A acts as a cosmic switchboard, illuminating accretion processes, the gathering of gas and dust spiraling into the black hole. When material falls inward, heating dramatically, it emits intense radiation across the